My name is Aaron Murakami, and this is March 30th. It's 12 o'clock Pacific Daylight Savings Time, and here in Spokane, Washington. And we're going to have Eric Dollard on the call. He's down there in Nevada, and Griffin Brock. He's going to be sharing a slideshow on some of his tube experiments or developments, and possibly some ELF stuff I think Eric mentioned. And I know Adrian Marsh, he's going to be sharing some on some updated amplifier or something dealing with the golden ratio discharge. I just briefly saw a message this morning. If Haka says join us, he may or may not have something to add. And there's Bruce Gavin, and if Justin Miller pops in here, Justin does a lot of the support with some of the behind the scenes projects and administration stuff with the EPD lab. So he might have some basic business updates. So first of all, thanks for joining the call. Let me see if there's some other people in here. I think I have to manually add everybody as they're joining. But EPD Labs is a 501c3 nonprofit corporation based out of Nevada. And so it's a charitable nonprofit, and it's runs off of donations. And donations pretty much covers all operating expenses. That includes building insurance, utilities, the phone bills. I mean, you name it. It also pays for parts and some get-together episodes. It does help sometimes with some travel and lodging for a bunch of these guys to get together down there at the facility in Tonopah, where every X amount of months everybody kind of gets together down there, or as many people as possible, to start kind of breaking into some of these projects and getting some progress moving along. We are in need of some donations right now. There's a couple cross arms that are needed. Eric can go into more detail on that. We got some quotes that were kind of outrageous with the shipping, but if you go to ericpdollard.com, and I'm gonna share that real quick. I can figure out how to minimize the screen here. There we go. I want to show where everybody's able to donate. Screen share here. So on ericpdollard.com, this website here is the official Eric Dollard website. If you go to the home page, you can scroll down. These are some blog posts that, and you can see some of the progress, being made on some of these projects. But over here in the main menu bar is this donate link. And if you click donate, you're able to donate by PayPal, by Bitcoin, or check or money order. You can send that to the address here in Spokane. Then I just sign those and send them down to the bank in Nevada. Recently found out not a lot of donations in Bitcoin. We looked it up, and there's about $250 worth of donations in there. Most people donate by PayPal. If you click this link, you can make a one-time donation of however much you're able to donate. But there's also a little checkbox if you want to make it recurring. So if you're able to make a $5 donation per month, $10, $25, $50 or more as an ongoing donation, that really helps a lot, and we really appreciate all those. Another website I want to share is emediapress.com. This is my main website, where all the conference presentations, the books are all posted. You can kind of scroll down, you can search in the main menu bar, author's name, or you can mouse over the shop link, and you can go down to the different year of the conference. And if you click on one of Eric's presentations, for example, this is one of the presentations he did at the last conference. Then you can scroll down and you can kind of see other related products. Depends on how good the keywords are, but you can click on the category Eric Dollard, and this is how you can easily search for presentations specifically by any particular author or presenter. So here's a whole compilation of or collection of Eric's presentations, and I think there might even be like a second page. So far this year, there's still no conference planned. I'd like to talk to these guys about possibly doing some type of weekend workshop thing, and if something we can coordinate, doing something down in Eric's shop down there in Tonopah, and maybe doing something up at my shop, because there is still a lot of unfinished projects at my shop with the RF the RF bay, and Adrian has brought a good amount of equipment there. So there's still a lot of things that we want to do there. You know, with or without a conference, we want to continue to bring these to completion as time permits, as the funding allows, and so forth. And let's see. I'm going to turn it over, stop the sharing here. I'm going to turn it over to Eric so that he can cover a few things he wants to go over. Let's see. Second, kind of trapped here. Okay, here's Eric.
One.
Yeah, go ahead, Eric. I'm trying to get your video pin, your screen pinned on the there you go. Okay, good. Yeah, go ahead, Eric, and then you can turn it over to Griffin after.
Yeah, so as far as what you got going up there, the next level is to get the modulator output voltage up approaching the 100 kilovolt level, which will take some rather bizarre inductances to achieve. But that's in order to do what was originally intended, which was to apply so much electrostatic force to water that it would break apart without drawing any energy from the power source. So there's complications with that, like anything else, because how do you get 100,000 volts of water not to violently act upon each other? Which involves insulating the plates with some kind of special material. But at any rate, the next thing in line with that, and I have a pair of 3,000 watt modulators here for producing 4-phase, is to get the voltage up to the 100 kilovolt order of magnitude for purpose here of the electrostatic induction motor, or the Trump motor. What I would like to accomplish here is to get a 10 or 15 horsepower machine. I have enough power in the 4-phase frequency converter set up with AM transmitters to produce something of that power, and it would be the only thing of its kind in the world. So that's one of the reasons for the AM transmitters here. And then, of course, Aaron's got a smaller so-called single-phase version of that. Then we have to finish getting the power level up to about 2 or 3 kilowatts on the RF, and get the cosmic induction generator powered up to the point that we can continue with the cosmic light bulb, so to speak, which I've thus far coded the OA1 cosmic light bulb. That will be an intensive experiment of controlling gas pressure and getting the bulb right and all that. So like the Trump motor, which is an engineering nightmare approaching an engineering impossibility, and the electrostatic water separation, which requires really bizarre plates, the OA1 cosmic light bulb will be a very arduous project. Here I spent the last month designing the IF bandpass filter for the ELF receiver that I'm designing, which will operate in conjunction with Griffin's dielectric aerial. There's all kinds of extremely difficult complications with that, in that the impedance of the aerial is infinite, so you can't use any kind of conventional networks or what have you to manipulate that signal. And also there can be days where that signal reaches a level that it would cause violent explosion and fire, so protection has to be installed for like lightning and what have you. So the filter was an interesting project. I'm wrapping it up now, in that I'm applying my my specific theory of electric wave propagation to the design and analysis of the filter, which is drawn from Terman's Radio Engineer Handbook. It's the most sophisticated filter in the chapter on filters, and the equation for it is 5 pages long. So to make the equation more sensible and to see all the necessary relations, I had to consume 250 pages just for the arithmetic. Thank God I have a calculator and I don't have to use a slide rule anymore, because this mathematics is so extended that 5-digit accuracy leaves you with about 98% of the desired value at the end of the process. So it's been quite a job, but I've learned an awful lot about the relationships between longitudinal and transverse propagation combined into a network structure. And then this will be the bandpass filter for the ELF receiver. Now, when I say ELF receiver, I don't think such a thing even exists presently. VLF is 3,000 cycles to 30 kilocycles. Ultra low frequency is 300 to 3,000 cycles per second, which is known as the voice frequency band. And then there's one more. There's ultra low, super low frequency, then would be from 300 to 30 cycles per second. And ELF is 30 cycles per second down to DC. Now, having a receiver that receives DC might be a crazy concept in many people's minds, but when you're dealing with things like seismographs and earth signals and what have you, you really have to have a receiver that goes down to DC, because the DC receiver captures the polarity of the DC, where a normal receiver, normal superheterodyne receiver, loses the polarity. So if you were to use a normal superheterodyne receiver for a seismograph, the pen would only go to either the right or the left of the center line, which would not be desirable. But with this particular type of superheterodyne receiver, which uses Tesla converters rather than the conventional multi-grid converters used in the front end of the receiver and in the BFO or product detector in the output of the receiver, we will be using Tesla converters, which is a high-speed reversing switch that switches from the antenna and then switches to the receiver and back and forth at a synchronous rate. So it's going to be quite a bit of effort to pull all this off. Things are the Tesla converter matching to the aerial is the main problem I'm facing right now, because I can't use conventional networks. So that's what's been going on at the expense of, I have not been working on the disassembly of the Bach music, nor have I been continuing with the second chapter or second chapter of the four-phase, which each chapter being a booklet. So chapter 1 is already out. So I'm working on chapter 2 now. So I have to get the Bach transcription and the book chapter out of the way before Griffin shows up, because he's going to scan all this stuff, because it's way too valuable to send through the mail. And then the side effect of the ELF receiver project is the amplifier project. So once I have all the data in, which has been slow in coming, so it's still got some blank spots because the mail's been so difficult. A lot of saboteurs in the postal system now, so that's delayed things. But the objective is to come up with some kind of universal, very high fidelity audio amplifier that will go from a musical instrument or a CD player into a set of headphones or a small loudspeaker. And it'll use a lot of the design concepts that I've developed out of the Bell Telephone Laboratories material, just like all the bandpass filter stuff. That's all Bell Telephone Laboratories material. In fact, I actually gave an entire presentation on it called Electrical Transmission and Multiple Coordinate Systems. So the key here is you can't use just a simple L, inductance, and Henry, and the C, capacitance, and farads anymore. You need 4 energy coefficients rather than 2. You also need the mutual inductance M and the mutual elastance K. So in Griffin's antenna, that electrostatic energy, so to speak, that's involved in the process between the antenna and the ionosphere is no longer in farads, but it's in per farads. So that's the elastance K, where the capacitance from the aerial to ground and the trees and the power lines and all that, which acts to short out the signal from the ionosphere, that's measured as the capacitance C in farads. So there's been somebody that's been asking a question over and over again on these YouTube things and what have you, and I tried to respond, but digital doesn't work for me. So the only way that I can respond to anybody's questions is they have to write me a letter, or I have to send a response to somebody like I used to do a decade ago, and then somebody enters that digitally. And but right now I don't have the manpower to do that. But the question is something that Chris Carson brought up in that ham radio society video that we did, probably 20 years ago, is when you have a transformer and you have, let's say, the same number of turns on the primary and secondary, and you have a core of infinite permeability, which would be ideal. You have windings of zero resistance. If you have 1 amp drawn out of the secondary, there's 1 amp drawn into the primary, but it's out of phase, going the opposite direction. So in a perfect transformer, when you have 2 currents which are in very close proximity to each other, with the current flowing in opposite directions, there's no magnetic field. So mutual inductance then is kind of an enigma. Where is it? Well, it's defined as that magnetism which surrounds the 2 conductors. And when you have 2 currents flowing in the opposite direction between 2 conductors, there's a magnemotive and a physical force that pushes the conductors together. So there's something there, but it's not magnetism that we're taught. It's not inductance type of magnetism. So this is the mutual magnetic induction or induction, so to speak, the mutual inductance, which has to be isolated out in the 4 energy storage coefficients of any complex transmission system. Of course, the one that's most difficult is the Tesla transformer, particularly the longer, skinnier ones like Adrian has. So to this date, nobody can define, no matter how hard they try, or even you put a gun to their head, they would not be able to define the propagation constant of that coil. It is mathematically indeterminate at this point, even though in that presentation that I mentioned, the electrical transmission and multiple coordinate systems, the basis for the mathematics and its application to the problem is pretty fully developed. And then there's another video that goes with it, the 20-to-1 scale replication of the Colorado transformer, that actually applies this mathematics to the analysis of the transformer and is in very close agreement with what Tesla had constructed. Now, an interesting sideline in this mutual inductance is my way back, my involvement with something called the integratron, which has no relationship whatsoever to what is called the integratron today, which is basically just some kind of, I won't even get into it. It requires too much vulgarity, but that should tell you enough. This goes back to, I got there shortly after Van Tassel died, and there was a readjustment period to get rid of all the negative forces, and then somehow the voodoo had charged me with trying to figure out how to get the first stage of it going, and I interviewing people and finding materials and reading things and what have you. I took it to that first level, and it involves something called the caduceus coil. And just recently, when somebody presented this question about, well, why does the mutual inductance theoretically not have a magnetic field, which would be exemplified by the fact even with a conventional transformer is the magnetism that's sensible in the transformer does not vary with the load. So obviously this mutual induction is something occult. But at any rate, Van Tassel employed a device called the caduceus coil, which doesn't seem to make sense in that you have a ferrite rod and then a winding goes up the coil clockwise and a winding comes back down the coil counterclockwise. Van Tassel points out the point of crossing, the angle of crossing must be 22.5 degrees, and he had a little assemblage of these coils with tags on them that gave numbers. I don't know all that. When Chris Carson died, a lot of that stuff disappeared, but I think Peter Lindemann has those coils. And those would not be called inductors, they would be called inductors, because there is going to be this mutual magnetic induction, so to speak, for the lack of a better word, in the core, and there will be a measurable impedance or reactance at its terminals. This would be in designing analog networks for producing high voltage or modeling Tesla transformers. This may turn out to be a component. So that kind of concludes what I have to say. And I guess Griffin can maybe give us a quick overview of this ELF and dielectric aerial and then show us his tube advancement.
Okay, I'll proceed with that. Let me share my screen. It says that you've disabled screen sharing, Aaron.
Yeah, hold on a second here.
Yep.
Okay, go ahead and try again.
Okay. Okay, can you see my screen? Can you see my screen?
Yeah, it looks good.
Okay. Okay, well, I'll proceed with the overview of the aerial flat top condition, which I've presented upon before. What I want to make note of is that all the detailed measurements which have been carried out thus far with the aerial flat top capacity, as well as further will be carried out, have been augmented by the current weather which my region is experiencing. So, of course, quantifying the characteristics of this flat top are still a work in progress once the rain and the storm has passed this part of California, as that does lead to erroneous results. But nonetheless, thus far, it's been possible to quantify using this setup the overall characteristics of this type of Marconi flat top antenna, which comprises multiple parallel conductors shorted upon themselves by a common bar, which could be seen in this diagram. We have a connecting copper rod, which extends itself a couple feet and hoists multiple conductors, and in essence acts as a uniform capacitive sheet suspended a specific height above ground. Now, in constructing this type of capacity, which I've touched on in prior calls, that the ability to quantify the surrounding interference, which is generated by various nonlinear loads, including LEDs, CFL lightings, and what have you, does impose a great burden on the reception of telluric activity. I've shown the oscillograms which I've obtained in the past using this flat top capacity with a electromechanical device or a Tesla converter, which ultimately allows you to receive these transients which are forming in this type of system, which comprises, of course, the flat top and a specific earth ground located a distance away. And by measuring these transients, this interference, we could quantify the ratio from interference to telluric signal activity. Now, in the course of my experiments with receiving these two signals, the unwanted and the desired signals, I've noted that on a regular day, there's an average of a 1:10 ratio of signal intensity between the interference, which is generally 10 times greater, than the desired telluric receiving signal. Excuse me. Now, of course, this does vary from day to day and from hour to hour, as the interference is not regular, but does present itself in a multitude of various ways and at different intervals during the day. But nonetheless, should the propagation characteristics of the surrounding, or I would say the propagation characteristics of the present day in which these types of measurements are being taken, that considering those optimal conditions, I have obtained that a 1:10 ratio exists between the interference and between the receiving or the desired telluric signals. Now, as time progresses and as time permits, I will be hooking up various apparatuses to this flat top, which will further characterize the condition between the Earth and the ionosphere using this unique aerial setup. And this should afford some rather interesting results. In the previous call, I've mentioned that I have constructed a replica of a Tesla coherer, which effectively measures lightning activity at varying degrees or varying distances. That has to be further quantified, but nonetheless, this type of a setup lends itself to that type of apparatus, as well as other receiving apparatuses involving the reception of telluric activity. So I do not have any further detail on this as any means to quantify the condition between this setup has been augmented by the weather, as I've said, but nonetheless, progress is still going forward. Now I will proceed with the tube developments, specifically the 1A21 tube. Now what could be seen here is the prototype development of a 1A21 tube socket. I want to point out that this type of tube socket, which is of experimental condition, is shown on the left. And we could see that there is a likeness to that of the long used 01A triode tube socket shown on the right. They are similar in the sense that they both employ a pin socket or a pin section, which is seen by this gap on the side of the socket. It enables the tube to be secured properly without it having to pop out, and could be mounted in a multitude of configurations. So the tube socket, which is shown on the left, comprises 4 holes on either corner, which is used to secure the socket to any base, and is not intended for the implementation of electrodes or binding posts as shown on the ancient or the long used socket on the right. This is merely a comparison to show that there is a similarity between the two designs. Showing the experimental vacuum tube socket, we see these 4 holes, these 4 mounting holes on either corner, as well as the center hole, which will encompass the securing pin or the female receptor to the bayonet mount of the 1A21 tube, which is similar to that of the early Westinghouse lamp socket, comprising only a single base, which affords itself to a multitude of various mounting schemes and allows the experimenter to do as he pleases with that type of socket, as it's rather universal. So this, of course, is the experimental base mounting scheme, which has been progressing forward. This type of base has been manufactured by Hawkesses, which he was not able to join on this call, but he wanted to showcase this picture of the various sockets which he's been constructing thus far. He has laid out a definite plan of using a type of injection molding to formulate these types of sockets. Nonetheless, these are very experimental in the sense that we still have to quantify just their overall voltage handling capabilities in the cases of, say, a undesired reaction with the applied potential to the tube, as well as its thermal rating and thermal handling, as the 1A21 tube does emit quite a bit of thermal radiation in the process of its operation. Now, one thing I want to point out is this tube, given its universal characteristic, could also be applied to the multitude of other vacuum tubes which I am currently developing that pertain to Nikola Tesla as well as William Crookes, in which a similar mounting scheme is employed. So this is why this type of socket is advisable, because it lends itself to a multitude of variation. Now, in touching on the 1A21 tube, I was enlightened by a colleague located in Canada that he is an academic who has access to a multitude of various scientific equipment and radiation equipment, that is, and he kindly purchased a 1A21 tube for me and conducted a series of experiments involving acquiring and measuring the overall spectra as emitted from the 1A21 tube. Here you are looking at a spectrograph of radiation output from the 1A21 tube, measured in units called kiloelectron volts with respect to a pulse height. A pulse height is an arbitrary quantification of the intensity of the output, but it is graphed with respect to the energy output, from what he tells me, shown on the x-axis, which is measured in kiloelectron volts. The unit of kiloelectron volts, as it's not exactly applicable to most experiments which I am involved with, does lend itself in this circumstance, as it is able to quantify the relative output intensity of the tube in an overall scheme. So we are looking at a energy range from approximately 0 kiloelectron volts to about 3,000 kiloelectron volts, or in other words, 3 million electron volts. Now, from this colleague and his determination, that he found that by placing this spectrometer apparatus, which is specifically a radio code 101 device, at a distance of 5 feet away from the tube, he determined that there are various peaks which correlate to upper UV spectra of radiation, not X-ray radiation, but upper UV spectra, which could be seen by this massive spike on the left-hand corner of the chart. This corresponds to an energy level of approximately 100 kiloelectron volts. But we could see that there is an anomaly occurring on the right side of this chart as well, near the 3,000 kiloelectron volt threshold, which does not correspond to any hard or soft X-ray emission, but rather something beyond hard or X-rays, which is rather unique because this is something you would not expect in the emission of a typical X-ray tube. Now, one thing I want to point out is that in the grand idea of the operatings of a typical X-ray tube, we see that there is a relationship between applied potential to the anode of an X-ray tube and to that of the output emission of the X-ray tube. So in essence, which this chart defines in a linear way by the blue line, that if we applied a potential of, let's just say arbitrarily, 100 kilovolts upon the anode of a conventional X-ray tube, we should receive a relative output of 100 kilovolts of X-ray emission. So this defines a linear relationship. But going back to the blown up image of this spectrometer reading, we see that there's an output emission at roughly 3 million electron volts, which does not make sense because the colleague who took this reading is operating the 1A21 tube at a potential of around 100 kilovolts to 200 kilovolts. Now, in doing so, we should see an approximate output energy reading of around 100 to 200 kilovolts if we were to analyze this as the emission of typical X-rays. Now, we do see an emission similar to that energy range between 100 to 200 kiloelectron volts by this peak, but it does not necessarily fit that rule necessarily, nor does this spike, which is occurring at the further end of the spectrum at 3 million electron volts, So this begs the question, where is this extra so-called energy deriving itself from? If we're operating the tube at only a couple hundred kilovolts, we are obtaining effectively energy emissions well beyond that. In essence, around 15 to 30-fold increase from our input level. So this is what gets into a very interesting topic of study because we are dealing with an unknown subject and really a compounding question upon question of how this tube is operating. Now, in my previous experiments, I have had experience with this type of energy increase in which I have operated primitive tubes, such as this one, with moderate potentials anywhere from 20 to 50 kilovolts at a specific frequency, which did not have any effect whatsoever on the tube's operation. And by doing so, I found that there was as well as a 15 to 30-fold increase in the overall electrostatic field strength emanating from the tube. So we could determine that this tube, in a way, is acting as an electrostatic intensifying setup, more or less, in which the beam which coalesces and forms from the tube's cathode is essentially amplifying itself from whatever applied potential is being supplied to the cathode and magnifying this many-fold. Now, in my previous experiments, I pondered whether this increase or this intensifying factor was proportional to the tube's geometry or the elongation of the tube, in which I successfully determined that this was the case, that the optimum condition for this type of radiating matter tube to manifest or to magnify an applied potential to a specific degree of maximum potency, more or less, was a glass envelope of about 4 to 7 inches in length. Now, the tube that you are seeing before you is an early tube in which its length extends well beyond 10 inches. And by constructing this tube, I was able to determine that the length does correspond to the maximum intensity of the tube. And this may lend itself to the factor of the tube being able to project its emissions thousands or hundreds of feet away in any distance through all matter, regardless of its density, in which this tube is amplifying the applied potential, which is able to correspond to the vast distances that this tube is able to traverse, its emissions, that is. So this was a rather interesting topic of interest that stunned me, as I have not performed any spectrometer readings of the emission from the tube, nor has anybody else to that effect that I'm aware of. So this colleague in Canada is still in contact with me, and he's still in the loop of showing me further information that he's going to uncover in the near future. So this was one of the first readings that he took only about a month ago, and he was telling me that these types of readings, which he has also been able to replicate and displays the same result, he was able to write a paper on this effect and has presented this to me within the last week. So I'm awaiting further results, which he is going to uncover, as well as any other individuals who are willing to take up this matter and see to it the further experimentation of this tube. So that was a generalization of the efforts which I have been endeavoring upon thus far. And
Can I point something out, Griffin?
what was that?
Is your graph, the peak that you tried to show is completely blocked out by all the little pictures of everybody on the side.
It is? Okay, let me see if
Well,
I can.
now I can see what you just did. You can see it, the top part, but you can't see the bottom.
Okay,
Go back to that one.
okay. Let me see if I could share my screen. Okay, can you see my screen?
No, see the photograph or the pictures of everybody.
How
I don't-
about now?
I don't know if
Okay.
everybody's experiencing the same thing, but there's a little one on the side
So
that I can
Eric,
see. It's like a vertical line.
Eric, I think, is it possible for viewers or people who are calling in to change their view? Like if you move your mouse to the top right of your screen, there should be a little thing that says view. I don't know if that's just what an admin sees. Do you
Are
see
you-
that, Griffin?
Are you able to see this this chart, all of it, Aaron? Or
No,
Adrian?
the thing to do, Griffin, the easiest thing to
Yes.
do is just make your presentation there so it's not full screen, and then just
Okay.
shift it to the left, and
Okay.
then everybody basically will be able to see the whole graph.
Can you see the graph now?
No, because it's still full screen.
Okay, let's try this again.
If you make it not full screen, then shift it over now, the whole window.
Okay,
Just shift the window over.
okay.
Other way,
Left or right?
it will be your left.
Okay. Okay, it is shifted all the way to the left.
Okay, but just as you were just scaling the size of the screen,
Yes.
just go to the bottom right-hand corner of
Okay.
the window and then scale it across. Keep going until I tell you to stop.
Okay. Because on my side it looks different. It's already the
That's
scale
okay.
is already to the right.
Keep scaling it if you can, Griffin.
Okay.
So, hey, Eric, can you move your mouse and let me know if you see something that says view? at
That's
the-
it.
Now I got
Griffin,
it.
Griffin,
Okay.
that's right.
Yeah.
That's
Okay,
perfect.
there we go. It looks different on my side because
Oh, that's really bizarre.
Okay, but hey, Eric, I still need an answer. If you can move your mouse on your screen, I just need a yes or no if you can see something that says view at the very top right of your screen. It'll say view.
Yeah.
Okay, if you click on view, there's different ways that it'll rearrange stuff on your screen. So if you click on the thing that says view, it might say like standard or
Yeah, but I don't want to do something and then I get stuck. I can see it now.
okay,
Me
So-
good.
too.
Yeah.
Me
So
too.
what those options do is it lets you see it how it's supposed to, rather than Griffin having to adjust it so that you can see it.
Okay.
But at any rate, now I can see it and it's crazy. It goes straight up.
Yes. So unfortunately,
But we don't know
It's-
what's past it because it's beyond the range of the instrument.
exactly.
indeed.
So I asked the colleague whether or not he could acquire any other sophisticated apparatuses which would extend itself beyond 3 million electron volts. So he's in the process of acquiring that. But nonetheless, this graph does indicate that there is a rather unusual and unconventional emission that's being generated, which, of course, any conventional theories that I know of thus far would not allow for any explanation of this to occur in the first place.
Well, actually, if there is if there's something like a fission process going on in the cathode,
Right.
that would cause a massive release of energy, which might very well occur at one specific frequency, for the lack of a better word.
Exactly.
What
And
might
it would be
what
like coherent light. I mean, that's basically what you got there. You got a laser output. It's one, well, I don't know if we can call kiloelectron volts frequency, but in a certain sense, I guess if you look at Planck's way of looking at things, you could say it's
related.
putting out a coherent oscillation at an energy level way beyond anything that the power supply is delivering. So there must be a nuclear fusion or a nuclear fission process going on in the cathode from the E equals MC squared way of thinking.
And that goes back to the linear relationship between the applied potential and that of the output intensity, that the general concept of an X-ray tube is that the emission cannot exceed the applied power going to the tube. But this very well is.
I should think that's more likely to be a fusion process going on. At such a high killer
Well, I
electron
mean,
volt.
that's a possible theory, but that's a conventional theory.
Yeah, it
That's
could
why
be. It
this
could
so-
be a fusion
Conventional
process.
theory. So like secondary emission on a cathode causes it to
Mhm.
liberate more amperes of electron flow than it would if there wasn't any secondary emission.
Mhm.
It could
It's certainly a very interesting result.
it could be something where there's some kind of atomic nuclear dissociation or reassociation going on that's giving rise to this completely anomalous output.
That's why I await further.
Whatever it is, it's out of the ordinary. This is what's nice thing about getting into Tesla stuff is you just popped open the hatch to a completely alternate universe.
Indeed. It definitely needs, Griffin, it definitely needs an additional measurement beyond that maximum 2916, huh?
Definitely. So that's why he's in the process of acquiring more rugged equipment. Apparently, he works alongside with a university, so he has access to these higher end pieces of equipment, and I await further information from him.
Well, it'd be nice to get one of these that's amplitude versus wavelengths rather than energy.
Hopefully he could procure one because
Yeah,
the ones I've seen, yes, the ones I've seen that do measure versus frequency are rather expensive and a bit difficult to come by. So hopefully he could uncover one.
Have you looked up, Griffin, approximately what that kilo electron volts corresponds to in the electromagnetic spectrum?
I do not have the chart right now at the present, but it would correspond to
what about any type of like gamma or beta radiation or what have you, because those things
I guess it's less than gamma.
Electron volts. What's that?
Yeah, I guess it's less than gamma, but maybe it sits somewhere between the X-ray and gamma spectrum.
And then this, of course, brings up the idea of whether these type of emanations inflict biological harm if they are within this spectrum. But as covered in my previous presentation at the last ESTC, as well as my own research and some others as well, that so far we cannot observe any biological mutation or adverse effects.
Well, my belief is what this is Tesla's cosmic ray.
Okay, I just looked up.
No longer X-rays or neutrons, or it's something completely different. It's I mean, this is my notion. I'm not saying this with any, you know.
I just looked up online.
Basis. What's that?
Eric, I just looked up online, and basically 2,900 kilo electron volts corresponds to that of a helium atom interaction during a fusion process.
Well, there we go.
Interesting.
That's 2,900 kilo electron volts.
Yeah,
right.
So that's pretty exciting. That's pretty exciting, Griffin. That's a pretty exciting result.
But well, especially if it goes beyond that.
Well, we need to see what goes beyond that.
Definitely.
We can't see that in that measurement.
Definitely.
But that's a helium atom interaction during a fusion process at 2,900 kilo electron volts.
Well, maybe now this is an aluminum atom going through a fusion process.
Yeah, possibly, yeah.
Yep, that's why I await further.
Didn't you determine, Griffin, that the weakening of the tube, the cathode depletion was in fact a depletion, that it's the contamination of the cathode that's being liberated, and when it's gone, the tube ceases to function?
Exactly. So I found that once the tube's intensity decreases upon its optimal operating condition, that the vacuum within the tube is not impaired, but the cathode itself gains a tarnished layer, and it appears that the cathode is deactivated, so to speak. It's no longer in its prime operating condition. And what I have done in the past is removed a tarnished cathode from an exhausted tube, cleaned it up by removing the tarnished layer with an abrasive, so restoring the aluminum back to its original finish, as this tarnish is merely a surface layer, and reinserting it into a new tube. Now, in doing so, I found that the tube's output intensity suffers severely. So in essence, the cathode is forever tarnished. It no longer works, even though that this is an observable surface condition.
So you could say, Griffin, that in some ways if that were a fusion process, then in some ways the fuel is spent.
Yeah, exactly. That's a possibility.
Mm-hmm. Very interesting.
And that completes my set of experiments, so I suppose I could hand it over to you, Adrian.
Thank you, Griffin. If you would just stop your screen share. Thank you. We look forward to further measurements, particularly at the higher killer electron volts, Griffin. That's very interesting. So
Okay.
I will share my screen. Do you see that?
Yeah, looks good.
Yes.
No thumbnails. Right.
Okay, good. So what I'm going to share today is some developments and experiments that I've been looking at in more detail in terms of tuning the golden ratio discharge experiment. This also corresponds very closely with something Eric was sharing earlier and something that we have been exploring a little bit so far in EPD labs. That is the condition for a coherent Tesla transformer. And Eric defined basically that the coherent condition for a Tesla transformer is where LMCK equals 1. Eric was speaking before about the inductance L, the capacitance C, the inductance M, and the elastance K. Those 4 fundamental energy storage systems within the Tesla transformer. And this got me thinking about how the tuning is working in the golden ratio discharge apparatus. And the approach that I had taken previously is that I had taken a somewhat standard approach to tuning the Tesla transformer. So I had first of all worked out roughly what the optimum inductance of the primary coil would be given the geometry, the very tall and skinny geometry that I have. It's a 5-to-1 geometry. And excuse me, after working out broadly the number of turns, which was 7 turns that I needed to apply to the primary coil, I then used a vacuum variable capacitor to do the rest of the fine tuning. And this produced a very good result. So I had always intended to return and look at that tuning in more detail in relation to the balance between LMCK. And this was my opportunity to do that. So I'm going to take you through the process of that, what I've done so far, and the quite considerably improved results that actually generates as a result of tuning in a slightly different way from normal. So just to review the apparatus, this is apparatus that I've shown quite a few times, but for those not familiar with it, from the left to the right, we have the coil system on the left here. That's a 5-to-1 standard Tesla coil arrangement. It's
Adrian? Are you intending to show the large screen, or just are you describing the thumbnails?
I am showing the large screen on my screen.
Are you okay? Does it?
There's a delay.
Is it showing the large screen on yours, Aaron?
I just see the folder with the thumbnails.
Yeah, that's what I'm getting.
Yeah.
Okay. Let me do this again then. That obviously didn't work.
There, I saw the big one for a moment.
So now you see the thumbnails. Now do you see this?
Yeah, there we go.
Yes. Yep. Now it's big.
Okay, good. All right. So just going back again, then the apparatus that I'm currently using at the moment, we'll just go through this to remind people. From left to right, on the left is the coil unit. That has the Tesla transformer. Its aspect ratio is very tall and slim. It's designed for, in this situation, for maximum voltage inversion. The primary coil is at the bottom, is the black region. This is the area that we're going to be looking at detail in this presentation. To the left is the feedback coil. So this is the coil here, which provides feedback to the grid leakage bias circuit of the vacuum tube. I'm going to be going into that more in detail as well. Below this is the vacuum variable capacitor. This is a 10 kilovolt KP14 Russian variable vacuum capacitor. Then we have the GU5B, single GU5B power oscillator. That's a Class C Armstrong oscillator. I will say a little bit about that in more detail in a moment. And then we have the high voltage anode supply here, which is a nominally 10 kilovolts, 5 kilowatt, and it can be run in a number of different ways. It's single phase, 4 transformers. Here you only see 2, and it can be run as DC, it can be run modulated, it can be run in a variety of different ways. So this is just to recap a little bit on the apparatus that I'm using. So if we move on from there, so this is the area that we're going to be looking at in detail today. So we see now I have a modified primary coil. So what I've done is I've created tap points on the primary. So 1 tap per turn. We see the tap here is that I can connect anywhere from turn 3 upwards to turn 14. Nominally before I was using just a wound primary with no tap points, and I had determined that about 7 turns was optimum based on my initial calculations and a empirical process of trial and error. But now we're going to have a look at a little bit, because the balance of LMCK is so important in terms of trying to move to the situation where we have a coherent Tesla transformer. Then now I'm going to investigate the effects of tuning in a slightly different way in more detail. So this is the area that we're going to be considering. This just shows in more detail quite an important facet of the safety device at the back here. This is a blocking capacitor. It's 25 kilovolts, 25 nanofarads with a spark gap, a safety gap on there, because this system is designed to pass very large transients, and we don't want those transients to go back into the power supply. And this combination of capacitor and spark gap, they absorb those transients that come back from the coil. So this is a very much simplified circuit diagram of what we have here, just to cover what we need to see from the tuning point of view. So B plus is the plate supply. It comes along, and we are essentially running the primary, the half-wave coil there as a parallel resonance circuit. So we have the primary coil here between 1 and 2, and this represents the primary tuning capacitor, the KP14, which is a nominally 1,000 picofarad vacuum variable capacitor. And that feeds directly down. Again, this is simplified. There are many other components involved in the details, but this is simplified just for clarity, down to the GU5B. And we can see the secondary coil here on the right is coupled to a feedback coil at the bottom, which is then fed through a grid bias leakage, which is what allows us to implement this as a power Armstrong oscillator, or Class C Armstrong oscillator. And the important point to note from this circuit diagram is that the primary here is being driven as in the parallel mode. And I'm going to come on to what that means in a moment. And I can make it simply in this way because I rely on the fact that the output impedance of the GU5B is also high. So the vacuum tube output, the anode potential with the current at maximum dissipation leads to an output impedance of in the region of about 2 to 3 kilo ohms. And that actually works very well in relation to the primary configuration of the inductor and the capacitor in the Tesla transformer. There are some other details that are missing from this diagram, but you can also do fine tuning of the impedance match by adding a variable resistor here as well in order to have fine control over the grid bias. So all of this leads to, let's have a look at what the impedance of this coil system actually looks like. Then we consider what it is we're going to be tuning to. So this.
Adrian, can I say something at this point?
Yes, please add something, Eric.
Yeah, this is something that flashed on me in all this network calculation where I'm mixing, the so-called series and parallel elements to get the desired result. Basically, the network, what do you call the device that draws these? Network analyzer?
Yes, this is a vector network analyzer.
Okay. It is only giving you half the picture. So there's one for impedance and there's also another one for admittance.
Correct, yes.
Now, the thing is by either one of those by itself does not give the characteristic of the coil. Is the impedance from the transmission standpoint, not in ohms, but zobles, is basically the impedance graph divided by the admittance graph, that quantity square root. And the propagation constant is the impedance graph multiplied by the admittance graph and the square root of that. So one is in radians per centimeter, and the other one then would be in either zobel or per zobel, not ohms. So that's kind of because I've noticed in the past that these graphs are misleading because you have to look at both of them simultaneously.
And that will definitely be a next development in being able to look at those two together.
How you could do that without having to go point by point, but I'm sure there's some computer program, that could figure all that out and give you the product and the ratio.
Okay, good. That's definitely a next step to investigate. Thank you, Eric. So just continuing to have a look at what we currently have here. So this shows impedance. So particularly it is Z11. So it's the impedance looking from the generator's perspective into the Tesla transformer. And the blue line indicates the magnitude of the impedance Z11, and the red line indicates the phase of Z11. And this is in the scenario where the coil is series fed. So in other words, we're looking just at the secondary coil here. We're not involving the primary in this. So in other words, the secondary coil sits on top of the hot output of the vector network analyzer, and the negative end of the vector network analyzer is connected to the ground system. So we immediately.
I hate interrupting you, but when I see something, I don't want to forget it. This graph shows the exact thing I'm talking about. You see the phase transference where it goes from negative to positive.
Yep.
Okay. This is where you need the admittance graph because you can't see its corresponding peak because it's zero. But the thing is you have to divide everything you see here into one. So that's not zero, it's infinity. You see how when you present it as impedance, it doesn't look like there's anything going on because it touches zero. But if you divide this whole thing into one, you see that?
It will become a peak. Yes.
Right.
This here will become a peak on the admittance.
Yeah, that's why.
Absolutely.
That's why somehow you have to incorporate both of them together, or you can't see what's going on.
Indeed. I would say if we were showing the series mode from admittance, it would be much clearer to see the peak that was happening. So we can see if we look at the fundamental series mode at marker 1 here, this is essentially where the impedance falls to minimum. or the admittance, of course, would be maximum, as Eric is just sharing with us, then we have an impedance here of 68.74 ohms. And as we would expect, the phase is 0. So in other words, it is at resonance, it's at the series resonance, and it is the real resistance of the coil at that frequency. We see the frequency is 3.28 megacycles. So that is the natural series mode of that coil. And of course, it has its associated parallel mode of the coil, which is this very sharp peak at marker point 2. And as we would expect, that has a very high impedance, so more than 225 kiloohms as it can be measured here, although it's actually much higher than that. Again, of course, it has a phase of 0 because it's actually it is a real resonance. It is a parallel resonant mode. And that's at 4.75 megacycles. So we see that there is a reasonable, considerable gap between the series and the parallel mode for this tall and skinny coil. So moving on, if we now introduce the primary, then we end up with this situation. We have a combination of the secondary coil and the primary coil. So we have one parallel mode comes from the primary coil, because the primary coil also has its own series and parallel modes. And we have one series and parallel mode. You don't see the series mode from the primary here. It's a much higher frequency, but we see the series and the parallel mode from the secondary. So we have decided here basically to put it in a balanced condition. So in other words, we've balanced the primary modes of the primary coil and the secondary coil. And we've done that by adjusting the vacuum variable capacitor to 214 picofarads, which balances the magnitude of the impedance of the parallel modes. That's markers 1 and 3. The series mode remains down here at 2. And we must also take into account this measurement is now primary fed. So the vector network analyzer is now feeding the primary coil. It is not a series fed measurement as in the previous one where we were just measuring the secondary. But this allows us now to look at both the primary coil and the secondary coil together as the generator would see them. So this is how the generator sees the impedance presented to it by the Tesla transformer. And if we have a look at the frequencies of these, so the series mode at 2, again, if this, as Eric has already pointed out, if this were admittance, we had here as well, this would be a strong peak in the admittance at marker 2 at 3.38 megacycles and 78.93 ohms. Again, they are all 0 phase. So in other words, they are real resistances at resonance. For the lower parallel mode at 3.09 megacycles, we have this peak, and the upper parallel mode at 3.78 megacycles. And it's these two parallel modes that we can take advantage of by using the Class C Armstrong oscillator. In the way that this system is matched, we're not able to take advantage of the tuning point at the series mode. We would need to have a different matching network, and we would need to configure it differently in order to be able to drive the GU5B at this point. So for this experiment, we are concerning ourselves about driving the tube system at 0.1 or 0.3, either the lower parallel mode or the upper parallel mode. And we can actually successfully drive at both of those modes, depending on how we tune. So moving on, we then tune ourselves into the situation where we're going to run at the lower parallel mode. So to do this, we have adjusted the primary tuning capacitor to 318 picofarads. And we see now that this has imbalanced the parallel modes. So in other words, we have loaded the system slightly in the primary, and this has accentuated the lower parallel mode. And this has now become stable oscillation point. This is now the stable position for the oscillator, and it will track this position. So as you tune the primary tuning capacitor, so the oscillator to a certain distance will track this point 1 here. And this is actually the point where I just show most of the results that I previously shown. It is a stable oscillation point at about 2.75 megacycles. And it shows the Golden Dragon very well according to various different tuning setups in the circuit, and also other conditions and characteristics of the coil and the way it's arranged. We see that the series mode remains largely unchanged. It's 3.4 megacycles, and the upper parallel mode is very much suppressed. So this is a stable oscillation point for the lower parallel mode of the system. This also, now we've retuned it to show the stable position for the upper parallel mode. So now we have reduced the primary tuning capacitor to 195 picofarads. And in effect, we've reduced the loading on the coil. We've slightly emphasized the parallel mode that is contributed by the primary coil. And now we see that the impedance is higher on the upper parallel mode. Now, the significance of the impedance being higher is it represents a better match to the tube. So the reason it forms a stable oscillating point is that the input impedance of the Tesla transformer is close to the output impedance of the tube. So it basically forms a point of maximum power transfer, and it also produces the point of stable oscillation. And we can adjust this 0.3. We can usually tune this over the region of about 200 to 300 kilocycles. And the tube will automatically track this point because it is the closest match to its own output impedance. So there is an advantage there to be able to track these upper and lower modes, and that also does affect the type of discharge that you get. So this condition will also show the Golden Dragon in this scenario, but it's also much changed. This is something that I've got into in much more detail in the past. So these are nominally the way in which the system has been tuned before, and I had considered that to be sufficient for this system up until we started exploring the coherent condition of LMCK equal to 1. So this raised in my mind, well, is it actually possible that by so rather than just adjusting through the vacuum variable capacitor and changing the tuning point, maybe I need to get the inductance, not the inductance, but the inductance more suitably, appropriately tuned to the complete coil system by adjusting around with the number of turns on the primary coil. So then I have 2 degrees of freedom for tuning, both the primary coil and the vacuum variable capacitor. Now, there is also some caution in adjusting in a high power system around the number of turns, because you are in effect also making considerable changes to L as well as M. And originally I had basically set up my system so that the magnetic coupling coefficient K was arranged between about 0.1 and 0.2, which empirically seemed to give the best effect for a tall and skinny coil and a relatively tightly coupled primary coil. But what I've discovered is that there are actually also some very fine tuning considerations to be done with the primary, not just with the vacuum variable capacitor. Even also, one has to be careful because the system is quite powerful and it produces quite a large induction field around it. One also has to be careful not to leave, for example, you can't just disconnect the vacuum variable capacitor and leave it open, because the displacement currents from the coil can actually cause an enormous voltages to appear on that open circuit capacitor. So I've also found that you need to short those capacitors together if they're not in use in the circuit. So for example, the vacuum variable capacitor, if we remember the original picture, was very closely positioned underneath the coil. Whilst that's very good in terms of connection, if you accidentally leave that capacitor open circuit, you can produce enormous voltages over there from the induction with the coil. So what I opted to do in this experiment, and I'll go back a few slides just to show, is I opted to use a fixed capacitance initially. So in other words, to put a 500 picofarad shunt capacitance and to remove the vacuum variable capacitor. I don't want to destroy the vacuum variable capacitor in the process of experimenting with the primary coil, because all of this system in this way, you can't tune it down at a few hundred watts. Its characteristics will change considerably from a few hundred watts up to several kilowatts. So really this is taking a tuning approach at much higher powers. And on that process, I wanted to use the fixed shunt capacitor, which is, shall we say, more expendable than the vacuum variable capacitor. The vacuum variable capacitor is considerably more expensive, whereas the shunt capacitor, I have a box of those, and if I happen to lose one of those from a nasty transient, from poor tuning, then that's more of an acceptable outcome. So I started this process using the fixed shunt capacitor, and then when I was happy with the tuning, then to go back to the vacuum variable capacitor. But that was why I was also adding in disconnecting the vacuum variable capacitor, I realized it was subsequent. It was incident for very high displacement currents coming off of the coil, and in that respect could generate very, very high potentials, which can lead to arc over inside the vacuum variable capacitor. So the irony of it is, even if you have the vacuum variable capacitor disconnected from the circuit, you might still destroy it if you haven't actually shorted the terminals. So moving onwards. So this is now a close-up of the coil itself. So the new primary coil that I put there, that's a 14 AWG silicone-coated microstranded Litz wire, which is particularly good in this scenario. It has many cores. There's about 500 cores inside that wire, which makes it excellent for this kind of higher frequency primary coil. And it is somewhat difficult configuration to build, but I managed to get a tap per turn, and these need to be offset from each other, as you end up with arc over across the coil. So they progress round the coil. I'll give another picture here. They progress round the coil, gradually the taps going up one turn at a time, and then it repeats once it gets to the 6th tap. So you end up with 12 available taps in order to finally adjust L and obviously make small changes to M. There's an overall view of how now the system looks. So my approach was to adjust one tap at a time, although that doesn't make a great difference on the small signal characteristics as you would measure. It makes considerable difference on the large signal characteristics when you actually drive it with the generator. This is also to note, the feedback coil is also intimately important in the process of the tuning the primary in this way. So this is a multi-tap feedback coil. This is the feedback coil which is taking a little bit from the oscillation in the secondary and is feeding that as positive feedback back to the generator. The GU5B is in an oscillator configuration. So I can change this one tap at a time. And that's quite important because the difference between one tap means that the tube oscillates very poorly or doesn't oscillate well, or can oscillate very smoothly. So there are quite a few degrees of freedom of tuning here. There is the Tesla transformer itself. There's the vacuum variable capacitor when it's so the parallel capacitance in the primary. There is also the taps on the primary coil. There is the taps on the feedback coil. There is the grid leakage bias adjustment and the grid bias adjustment. So we are playing with all of those degrees of freedom in order to find the best and most harmonious, or if we can say the most coherent oscillation that this system and this geometry is capable of. So what are the results of that? Well, when I played around considerably with the tuning, I determined that 5 turns, not 7 turns, was actually optimal on the primary. This is entirely determined empirically. And then I was able to put my vacuum variable capacitor back in and do some very fine tuning. And the results of the final discharge, these discharges were taken running at about 4 kilowatts, 4 to 5 kilowatts of power, input power to the plate supply, are 25% to 30% bigger and more developed and with more quality than they were before. So it was a considerable advantage to approaching the primary in this way. This is in the order of almost 2 foot high and shows considerable fine detail now, with all of the extra filaments and everything which we were not able to attain before this additional tuning step. We can see the beauty of this golden ratio discharge, how it forms primary, secondary, and tertiary tendrils, and all the microfilament tendrils, and they all follow the same geometric algorithmic proportion, which comes basically, it's a fractal expanding at the golden ratio. This is again all as a result of this tuning experiment. We get both high versus also things that are almost what you might call a mirror reflection. So if you were to put a mirror down the center, there is an uncanny mirror reflection to the left and the right of the discharge. This one's a typical golden dragon. It's difficult, it's different rather, and this one I'm not using the modulation that I presented on last time. If you add then the modulation to this, which is an additional step, and I may show that in the future, then you find that this discharge starts to extend further out of the tip and forms the much more beautiful and balanced and reciprocal golden dragon that I showed on the last live call. Again, the fine detail. Now, I found in this tuning method to try to obtain this system into a more coherent, so as coherent as it can be. I mean, clearly this coil, when I look at the distance between the parallel and serial modes, this coil is as tall and skinny is not what you would call a coherent coil. In actual fact, it's far from that. This is something that we were discussing with Eric. Eric, you might say a little bit more about this because you wrote to me on the LMCK equals 1 as being the optimum coherent condition, and there are it will be interesting to determine the geometry of the Tesla transformer and the electrical and mechanical characteristics that actually get you as close to LMCK equals 1. Do you have any additional comments on that, Eric?
Not right off, but it's a very difficult process.
Yes, indeed.
Some of it can be done by loading, in other words, adding more elastance to the output terminal or more inductance to the neutral terminal, or putting a parallel resonant circuit in the neutral terminal of very low characteristic impedance. Of course, that's going to require some monstrous vacuum capacitors. To get to the series mode, which I think basically is the best starting point, to get the coherence thing, you have to have a quarter wave matching network to go between the tube and the
Absolutely.
The ham radio people call that the pi output network.
The pi hour, yeah. That's my next step.
Yeah, that's essential for the the so-called parallel resonant mode, you would use a half-wave pi network, and for the series resonant mode, you would use a quarter-wave pi network. Ultimately, the problem is to do a proper scientific analysis of the coil propagation and all that. The fact that you're using a neutral and there's no such thing as ground at these frequencies, unless you brought it out here to the telluric test platform, then you would have ground. You have to use two coils in series.
Mhm.
Then the coils are isolated from any external influences other than what reactance network you put in between the low ends of the coils and what kind of extension you put on the output end of the coils.
Do you mean using the two coils as a reciprocal with a counterpoise?
Yeah, that way then you have a point of infinite admittance right in between the two coils.
Mhm.
So right now you can't get a point of infinite admittance, which is required at one end of the coil for the thing to really operate, in the mode that you want, where there's no voltage at the ground end and maximum voltage at the high end. So we have discussed the counterpoise. That's one way to balance the inductions of the coil is with the counterpoise, because the ratio of the capacitance, or more properly, the product of the elastance on the high side of the coil and the capacitance on the low side of the coil should equal the square of the characteristic capacitance of the coil itself. Are you starting to get an idea of how convoluted this process is?
Indeed. Indeed.
So, but mathematically, my experimentation with, these filter networks and all that in a lumped network form, this stuff is relatively easy to engineer.
Yep.
You can come up with a number of analog circuits for various situations, but the analog circuit, which involves distributed mutual inductions, is rather difficult. But I did come up with, in the Colorado Springs replication video, that circuit was developed. Also, my advanced Alexanderson antenna that I used at Landers, that also was LCMK. The product of all four of those equaled 1. So you can do it with series resonant, parallel resonant. You'd have to start. I don't know. Are you familiar with all that Bell telephone network design filter stuff?
I am, yes. I mean, I'm in the process of putting together a pi-owl network for this apparatus, so it can run at the series mode.
Yeah. So, but basically, that video, electrical transmission of multiple coordinate systems, which we watched, the introduction to,
Yes.
that's
Yes.
basically a 4-year college course on the subject. Everything you need to know is in there. And that combined with the Colorado Springs, but it is a 4-year college course. But it's very thorough. It starts, with this and parallel and what have you. Can we go to your circuit diagram? There's some things I noticed in there that
Sure.
that didn't quite look right.
Eric, let me just finish the last slide, and then I'll go back to the other.
Yeah.
So some more really nice pictures of these discharges. These have really become quite large now and quite sophisticated. Here's a very nice one where you've got two wound around each other. And that's, I don't know if you can see that. That's a video. I don't know if that will come out.
Yeah, it's looking good.
Oh, that comes out, does it?
Yeah.
Oh, okay. Then in that case, I'll show it. I've got a slow motion one too. I didn't think this would come out. So there is the actual process of it running. And I will show the next one, which is the slow motion of that. This is 10%. So slow down to 10%. And that's probably enough now.
Yeah.
Okay, good. All right, let me go back then, Eric. So that's the normally the end of the presentation. Let me go back to the circuit diagram you wanted to see.
Okay. So the grid rheostat and its bypass condenser.
This is the grid leakage bias circuit. Yep.
Yeah, that's on the wrong side of the feedback coil. Should be on the other side.
You mean down in position
Wrong
2
there.
here?
Yeah. That
And
way-
what difference will that make, Eric?
Well, it doesn't have all that RF floating on it. So the grid isn't, it doesn't act like an antenna feeding undesirable stuff into the grid, and it doesn't feed into other circuitry by being hot.
Will it still be an Armstrong oscillator in that case?
Yeah.
Okay, good.
See, the thing is that's the DC part, but you put the DC part on the AC side of the coil.
Mhm.
It's supposed to be on the DC side of the coil.
Okay. So then this section here can then move down to position 2.
Yeah, that's where it belongs.
And then in effect, the coil then connects just directly through the grid bias resistor, which is not shown here.
Yeah, through like a 1 ohm non-inductive parasitic suppressor or some kind of
Yeah.
lossy network. Like, remember I wound that rusty iron wire into like a little
I remember.
spring?
Yes,
Yeah,
I remember.
You should have some kind of resistance network there.
Okay, good.
Series
Okay,
resistance. But as close to the grid as possible.
I mean, I do have a series resistance rheostat there because that allows me to adjust grid bias.
You don't want that. No, you don't want anything that has any, like, excessive capacitance or radiating capability or whatever.
But it does help adjust the grid bias, though. It makes a difference in adjusting the grid bias.
But that's supposed to be on the other side.
Okay.
But yeah, I mean, you could put one there, but then, it's not DC anymore, it's AC. So that's basically what your parasitic suppressor does. But the thing is, it would have too much self-capacitance to serve as a good parasitic suppressor. In fact, it could make things worse.
Okay.
Introducing, and one other thing is go to the top part. Yeah. Okay, the DC side of the primary deal.
Here?
Yeah.
So the DC side will be here. You mean on the plate supply?
Terminal number 1, yeah.
Yeah.
There should be a 0.01 mica capacitor, or I suppose ceramic would work, that connects from that point down to the system neutral at the bottom.
I mean, there is. This is simplified. Remember, I have that big blocking capacitor is here.
Yeah, but there still should be one right next, as close as possible to the tube.
Okay. And that would be a mica capacitor.
So basically, you want to make sure that both sides of that primary coil, there's no, that all the leads leaving it tend to be close and parallel. And as soon as you can, as the closest point that you can get the DC side of the primary coil connected, not with an oil capacitor, but preferably with a mica capacitor, directly to the system neutral, the horizontal line there on the bottom.
So that's 0.1.
Yeah.
Point 1 here, down to the horizontal line here.
Yeah, right.
And as close to the primary resonance circuit as possible.
Right. You don't want extra inductance or anything there.
Sure. And that's about what did you say, 100 nanofarad?
And nanofarads were invented in my day. 0.01.
0.01. Okay.
Yeah.
10 nanofarad.
Yeah, that
okay.
would be 10 nanofarads.
Okay, good. Okay,
now,
excellent.
Ideally, it would be connected to the filament of the tube. But
so down to this point here, C1 or C2.
Yeah, because basically you want that tank circuit, you want that thing AC wise connected in parallel in every sense of the word, as close to that tube as possible. And that eliminates, see, before, that's why you had to add that oil capacitor is the primary circuit was only part of the total series reactance. You had all the leads, you had the power supply.
Correct. Yes.
So what you were
Yep.
doing, you were just lighting everything up. And then the final thing is, it is not a good idea to connect the neutral side of the secondary coil to the neutral of your oscillator or what have you, because then that's going to add some other feedback pattern, which
They're
actually,
not.
it might
They're
be
not.
this advantage.
This is actually this is misleading because they are not connected now.
Okay.
This does show that they're connected, but do you remember that we did all the experiments with the Colorado Springs and the hybrid system, and we put it down to the metal surface of the
Bench.
that's it's now running. It's now running like that. So if I go back, you see there's now a metal sheet at the bottom.
Okay. Yeah.
So the same like we did, the base of the secondary coil is just connected to that metal sheet, and that metal sheet is floating from everything else.
Okay, that's good. So there's going to be an optimum size to that.
Yeah, it needs to be bigger than it is
Yeah,
now.
now what you can do is what I would be inclined to do in blind experimentation, but it would give you some level of reactance control. This is how Aaron's setup, his half-wave setup is going to be with the 2 pi networks on either side of the phase, is I put a vacuum variable capacitor in series with the neutral lead.
Series with the neutral lead. Okay.
That way you can adjust the capacitance on that side. And also you could make a mask that you could adjust the elastance on the high side. Basically, anytime a capacitor is used in series, it's an elastance.
Mm-hmm.
Anytime an inductance is used in
so it affects K.
Yeah,
so
then it's an inductance. But anytime you have an inductance in parallel, then that's inductance.
Mm-hmm.
And when you have a capacitance in parallel, then that's the capacitance. So series for the inductance and series for the elastance, that's your series resonant mode.
Mm-hmm.
And then the parallel combination of the mutual inductance and the capacitance, that's your parallel resonant mode. But as far as network analysis goes, it's very misleading to do that. Because if you label your components somewhat differently, where you keep inductance and capacitance in one coordinate and inductance and elastance in another coordinate, then you have 2 T networks. You either have the series elastance and shunt inductance, which is your longitudinal mode, and then you have your series inductance and shunt capacitance, which is your transverse mode, and that's a more accurate way to look at it. And then ultimately, when you get involved with differential equations, then I think that little drawing I scribbled, that drawing was kind of in the midst of my network analysis.
Uh-huh.
I was looking for that relationship, and then so you got one of my scratch sheets.
This one here.
Yeah. So that's
this one is where you were talking to me about the coherent LMCK = 1.
Yeah. So you see, there's also the magnetic distribution, which is basically the product of the inductance and inductance, LM. And then there's the dielectric propagation or distribution, which is the series elastance and the shunt capacitance. So that would be CK. So CK and LM, they are an exponential distribution of the magnetism and the dielectricity along the length of the coil. So what it is now is you have a type of resonance where you have complex inductance and you have complex capacitance. You see what I'm getting at?
Mm-hmm.
So you can take all of that all the way back to the Heaviside equation, where there's also four constants, but 2 of them are energy dissipation constants, but the geometry is all the same. So there's the Heaviside condition where RC equals LG.
Mm-hmm.
And that's the point in which you have the so-called coherence, except now the resistance has been replaced by inductance, and the capacitance has been, or the conductance has been replaced by the elastance, if you can get that whole I know it's not going to be crystal clear, but I think you see what I'm heading towards.
Yes, yes, indeed.
So the
It's a-
question is how do you determine the distribution of magnetism and the distribution of dielectricity along the length of the coil, which you use those as your operators in your exponential equation to give you the resultant propagation on the coil? That ultimately, when you're dealing with substation transformers and what have you, that's the best way to deal with it. I don't know if you had a chance to look at that Bewley chapter yet with the 8th order differential equation.
I have started it, yes.
Yeah. Well,
It's quite heavy.
Yeah, I spent about 10 years on those two
I was
chapters.
going to say it's quite heavy. Let's say I've made a start.
Yeah, it'll take about a year.
Yeah.
Because basically you got to, you have to kind of take the stuff down, take it apart, put it together and experiment with it yourself.
Yeah, indeed.
And it does not use a simplified approach. It's like all these guys, they start from the most complicated approach rather than the simple one, where in my Tesla Colorado Springs replication video, I go from the simple to the more complicated, which I think is a better way to do it.
Mm-hmm.
But in general, that said, when you show the vector network analyzer, always show the admittance and the impedance together.
Okay, I will make sure that we actually I will show those graphs in the next live call, and then we can take a look at those together.
Yeah, do you have a way that you can multiply and divide them and then square root that result to get the actual constants of the coil?
We can. I'm sure there is a way. I'm sure we can find a way to do that because that's about the software.
Well, that would be quite an expansion of the application of that device, because then it can measure characteristic impedance. You can't measure characteristic impedance by measuring terminal impedance.
Mm-hmm.
You can only measure characteristic impedance by taking the ratio of the impedance to the admittance and square rooting it.
Mm-hmm.
Because characteristic impedance is not measured in ohms. That's unfortunately that's what we're stuck with, is all this. I mean, it's reached a depth where my landlord is the Bureau of Land Management, but if I say BLM, it means something else.
Yeah.
And people use the word Faraday cage completely indiscriminately. In fact, they use it in the opposite way that Faraday intended. So a Faraday screen allows electromagnetism to pass through it freely without any impedance or attenuation. It only removes the electrostatic component. So when somebody says Faraday cage, that means they don't know what they're talking about, and people with very high titles next to their name use the word Faraday cage in that manner. So I think that would indicate the dilemma that we have when we're trying to talk about these things. Another thing is when you look on a substation transformer and it's got a delta to Y transformation, which many of them do, its vector diagram shows you that the two are 30 degrees out of phase. That's absolutely incorrect. They're 90 degrees out of phase. It's just that 90 degrees minus 120 degrees is 30. And everybody has it wrong to this day. So how can you keep phase in a complex system, phase A, at the end of the line, when you say that the transformer is twisting it one way and it's actually twisting it the other way, 120 degrees off? We're filled with these complications. Ultimately, at this point in history, no one has a clue of the subject we're talking about.
Evidently.
So I guess that makes us anomalous.
And unique.
Hey, Adrian.
Yes.
Bruce here.
Hi, Bruce.
Hi. Great pictures, by the way. Really great.
Thank you. Thank you.
A couple of points, 3 points that came to mind. The vector network analyzer readings you get, they must be altered quite a bit when the system's under power. And I'm wondering,
there is a difference between the large signal and small signal analysis.
Yeah, okay, but the relationships hold, you're quite certain about that?
Oh yeah. I mean, Definitely at first order. So let me share a screen again, because it's an important point that you raise, actually, Bruce. So do you see that again now? Can you see the trace?
Yes.
So if I say progress here, this is one of the very stable operating points that I use in this system. So according to the vector network analysis, the stable oscillating point would be at 2.75 megacycles. And when I run that large signal, it is actually running at 2.75 megacycles or thereabouts, 2.76, 2.74. So the measurements that you take here in terms of first order frequency, where these events and anomalies are happening, is where it's operating at. You can then go and measure that during it's actually running. So when it's actually producing those golden dragon discharges, then, for example, I have a spectrum analyzer sitting some distance away with an antenna on it, and that is actually picking up accurately the frequency that's being emanated off of that, and it is at the resonant frequency. Or you can use, for example, the very high power differential voltage probe that I have, 100 kilovolt differential voltage probe, and I put that direct, which is a very low loading to the primary, put that onto the primary and measure that on an oscilloscope, and it is actually oscillating at the right frequency. So, and as you adjust it either way, so the frequency changes. So this is really just giving you an overall of how the envelope of the impedance varies with frequency. And the system operates in that way. I mean, that was how I first discovered that system was running at the parallel mode, not at the series mode. Because initially, when I first set this up years and years and years ago, I thought the system was running at the series mode, but it's not. It's not running at the series mode. It's running at the parallel mode. And which is, of course, obvious now, because the output impedance of the parallel mode is a much closer match to the tubed output impedance. So it naturally forms a stable oscillator based upon the balance of output and input impedance at the frequency that it's running at. Whereas with a series mode, like with a pi L, if I was to put a pi L matching network on the output of that tube, then I would be matching to a very low impedance. So I would be matching, I would be transforming typically like you do with a ham radio linear amplifier. You're transforming down from an output impedance of somewhere around about 2 kiloohms for, say, two tubes in parallel, like, say, two 3500Zs or 4400As, running at about 2,500 kiloohms in parallel output impedance. You're transforming that down to 50 ohms through a pi L network. So then I would actually be driving this system very closely here to the series mode, which is at 78.33 ohms. And that would then correspond quite accurately with the frequency at 0.2. So whilst you're correct in saying that there are differences, significant differences between the small signal and the large signal situation, the overall first order event of the impedance versus frequencies matches well how the system actually runs. That's what I found anyway.
So what your pi network is doing is not totally accurate to say that it's changing from one impedance to another, particularly at a quarter wave. At a quarter wave, what it's doing is it's converting from a high impedance to a high admittance. Because
but isn't that the same as saying? But isn't that the same as saying it's transforming to a high impedance to a low impedance?
Well, but see, the thing is, we're not talking about impedance in ohms. We're talking about impedance in zobels. It's a whole different thing.
Uh-huh.
The impedance in zobels is the square of the measured impedance. It's the measured impedance divided by the measured admittance square rooted.
Mm-hmm.
Which obviously is not equal to the Z in the Z over Y, because that's in ohms. But the characteristic impedance or the characteristic admittance is not in ohms. It's the best you could say, it's ohm squared square rooted. What, you know, anytime that you go through a square or a square root, you've gone through the looking glass. So you can't use the same names on one side that you used on the other. So this is something that's been completely kind of glossed over, you know, because nobody
Yeah.
learns this stuff anymore.
Yeah.
It's when you say impedance, you always have to keep in mind a corresponding admittance.
Hmm.
So a point of zero admittance is a point of infinite impedance. Well, infinite impedance is undefined, but zero admittance is defined because it's a point on your graph, but a point of infinite impedance on the graph doesn't have a point on the graph. So you have to go in certain situations, you have to do all your work in admittance, and in other situations, you have to do all your work in impedance. You see what I'm getting at?
It is. Normally, I must say, I mean, I'm displaying these vector network analysis results in a linear fashion. Normally, I would look at these on a Smith chart. So in other words, if I want to see really how it matches and what the transformation is of the network, then I would look at this on a Smith chart.
Yeah, but they're kind of abstract. If you can figure out a way to take a product of the two magnitudes and square root it, and the ratio of the two magnitudes and square root it, then you got the result you're after without having to track along a Smith chart.
Uh-huh. Well, that's an interesting development. That's something that we definitely need to try, and then we can show
the
it.
Smith chart has its application is in the matching network. It's going from an impedance to admittance, or
Well, it definitely works because I mean I use
Yeah.
them myself. So I mean it definitely works in terms of
yeah,
matching.
in the matching network. But see, the thing is I'm doing all this stuff not from an electronics engineering standpoint. I'm doing from an electrical engineering standpoint.
That's somewhere where we meet in the middle because I was
And
originally an RF and microwave engineer.
Yeah, but the thing is, it's still alternating current.
Indeed, exactly. In the scenario, yeah.
It's still electricity. There's no electronics involved. That was my revelation, you know, upon getting involved with Steinmetz, is electronics has got everything wrong. And there's no way you can get any understanding of electricity out of the portrayals and dictates of electronics. And that is why the power grid is going gangrene energy, or you might say it's discharging digital mucus into our environment, is because it now is in the hands of electronic digital people that have zero understanding of electricity. All they know about electricity is myths and adages and rumors. And so they're incapable of electrical engineering. And this is an electrical process that we're dealing with. The electronics now is when you get into the tube. Then it's a different story. Then you got to deal with its world. That's electronics. That's what we're up against here. So what I'm trying to do basically here at this instant is to steer our study of electricity away from electronics and back into electricity without stepping on too many toes. And that's what I've been busy doing for the past month, to the tune of 250 pages of arithmetic and 60 pages of finished drawings, which when they end up in the hands of Griffin, then they'll get sent to you.
Are you done with the slideshow, Adrian?
Say again, Aaron?
Are you done with the slideshow?
Yes, I have. Yes, I think. Just let me check, Bruce. Was there more you wanted to? Was there more you wanted to say?
Well, just a couple of quick points.
Yeah, you said you had a couple of points. Yeah.
Yeah, there's two other ones regarding the setup. I too built a circuit like that some years ago, and it was a 5-to-1 secondary ratio, but it was 12 inches, you know, a foot wide and 5 feet tall, and operated at about 110 kilohertz. And it was a lower power system, but I did do quite a bit of experimentation with the coupling between primary, which was a flat spiral, and the secondary. And if it was loose enough, looking at the spectral display from emitted in the area, in the local area, I could see those double humps that represent the two parallel modes disappear. They never showed up, yet the thing was still in resonance. So I was always under the impression that you'd wanted to adjust that coupling factor to get away from those two double humps. And so that's how I operated that. But the other thing, just as a footnote for design,
just as a point on that, Bruce, before you go on, is also remember if the coupling is loose enough, then the vector network analyzer is putting in a very small power. So I mean, it's not going to pick up the response when you put in 0 dBm. There's
a way around that. What you got to do is you have to proportion the ampere turns or the magnemotive force by having, less, even though the coil is bigger, you bring the inductance down and you bring the capacitance up. So what little coupling there is a lot more effective. If you see what I'm getting at?
Yeah, it's a good suggestion.
Because it is essential to get rid of that double peak, because the whole idea when you're doing this kind of stuff, if you have any other modes possible in what you're trying to do other than the mode that you desire, they're parasitic and they rob from the basic ability of the system to operate at its highest level of conversion or efficiency.
Not in this system. This system is running at those parallel modes. It's using them
there's
constructively.
But the thing is when you get rid of them, you'll find out that you'll get a lot more power. The thing
that's good.
More effectively.
Yeah, no, that's a good development. So
yeah,
I mean,
those are. I mean, that's something I know from like cavity resonators and klystrons and things like that. Is the problem with waveguides is they have transverse and longitudinal modes, just like a Tesla transformer does. And you don't want any other modes than the one desired for propagation, or what it does is then it robs from that mode which is propagating, and their transmission characteristics become less than desirable.
Apart from one thing that I would add is that the golden ratio discharge is actually, or the golden ratio discharge is a product of the interaction between those modes. So it's actually important to have that. If you take any one of those modes,
that's not true, because I got those golden ratio discharges very effectively by balancing the system where there was only one mode, the series mode, and the other ones were suppressed.
But did you know whether the parallel modes were there or not? Most people don't even know whether they're there or not.
Well, I did what Bruce did and got the coupling down. And then
getting the coupling down just means he wasn't able to measure it. It doesn't mean that it wasn't there.
No, I was measuring it. I was measuring it at the high power level with a spectrum analyzer.
Well, in my case, I basically just neutralized them out, so that it only had one. But of course, at that point in history, I did not have any of these network analyzers or what have you. But I know as a matter of fact that in any system that you want to operate at one specific mode, you want to suppress all the other modes. That's the whole basis for the Heaviside criteria. Is you don't want the dielectric time constant to be different than the magnetic time constant. If they both don't dampen out together when you pull the plug, well, then you got two modes. But if they're equal to each other, if the dielectric time constant and the magnetic time constant are equal to each other, then they merge into one mode, and then you get distortionless transmission. So multiple modes are undesirable, and they have to be suppressed. And that's the reason for trying to get all four.
What's your schedule looking like?
Get all four inductions to, how would you say, cooperate to get the maximum ability of the coil. So this is something that Bruce Gavin's been pointing out and this has always been, and anytime you're working with circuits that have the possibility of more than one mode, is when you have too tight a coupling, then that splits the modes, and you don't want that. So you have to back the coupling off So as far as your variable M goes, it's not so much the number of turns, even though by changing your primary LC ratio, you definitely got the discharges to develop much more sophisticated patterning than it had in the past. But to be variable M, you have to have like one of those old wireless days, you know, where they had the coils came apart and went together to adjust the primary, secondary. What would they call them? Loose couplers.
Mm-hmm.
And you the magnification factor has to be a lot higher. So in this case, you know, the RF current out of the tube may be 0.5 amp, and it may be 5 amps flowing in the primary. But as you loosen the coupling, you want to bring the primary inductance down and the primary capacitance up. So the 0.5 milliamp out of the tube now becomes 50 amps. You see what I'm getting at?
Indeed.
So this is what Bruce is arriving at experimentally. Now, my approach has always been to series feed, but then there's two problems with series feeding. Either you have to use a transformer, and ferrites, I've determined, are very poor mutual inductance devices. They're great for self-inductance, but they're lousy for mutual inductance, even though with what Griffin and I have done here, we've gotten some really good matches. The best way to do it is with a pi network, but the problem is when you use a pi network, then your neutral is connected to whatever other neutrals in the system, and you start getting all this RF feedback. So basically, the best way to do it is to have an actual transmitter with the output pi circuit or what have you, but also to have one of those variable link couplers so that you can kind of draw the power out of the tank circuit at the right amount.
You mean a swing link coupler?
Yeah, and the advantage, that's originally what I did when I modified my first RCA transmitter in my parents' garage. I had a 3 kilowatt transmitter in the garage and a 10 kilowatt DC supply that together were the terror of the neighborhood. And what I had the variable coil. What it was is I compressed it and expanded it. That was the best I could do to get the optimum, and that gave me the isolation so that I had 2 terminals out that didn't necessarily require a ground. Then that can go to the Tesla neutral, and then whatever it's using as a counterpoise, so it doesn't feed back into the system. So I think that's about all I have to say on that, even though it's so complicated, I probably could go on forever.
Well, it's a very interesting area.
Yeah, but it is a very complicated situation.
There are so many degrees of freedom to adjust and everything.
So basically, it seems to me like an improvement that you could do, which requires some rather substantial modification, is to build a larger, more intense magnet motive force primary circuit, and then which would have a large diameter, and then find that point in which you've gone to the critical point where the 2 sidebands eventually merge on each other and become coherent.
Mm-hmm.
And that's what Bruce is doing, but that introduces a lot of more mechanical and electromagnetic compatibility problems, because when you have a large diameter coil, then of course you've got a larger volume magnetic field that wants to get into things, and so you're kind of at the point. This is what has to be done for Aaron's unit, and this is the way that I've always done it out at RCA, is you have an open wire transmission line that goes from the transmitter to a platform that has all the Tesla stuff on it, and keep it all away from the transmitter. That way, I had a 5-turn coil that had 10,000 volts AC across it and 60 amps flow. Wow. That thing, when you brought that thing in resonance, the plate current went from 5 amps down to 50. So that's pretty good efficiency to go from 5 amps, not dipped out, down to 50, but you couldn't even see it on the meter. And you could just feel it come to life. Literally.
I'm sure.
I take a big, for audiences, I take a big piece of 2-inch angle iron and I bring it near that big giant primary coil. I think there's still a picture of it floats around on the internet of me holding, my hand on one end and somebody else holding a hand on the other, and we have a 25-watt light bulb between us, and you can see those big turns on there.
Uh-huh.
Yeah. I put that angle iron, I get that about 2 feet away from that coil, and watch the plate current meter go up, and in 5 minutes it'd be red hot. So I think that's an improvement, is to follow the path that Bruce has been taking and come up with a much more magnemotive primary and loosen the coupling, and then deal with all the complications that introduces.
Oh, good.
But
Bruce,
for actual scientific measurements, you have to use a half-wave coil. You have to get rid of all the parasitic reactances and susceptances coming in through the neutral lead, because there is no ground. At these frequencies, there is no. Try finding a ground at 100 megacycles. How are you going to do that? 1 inch of wire at 100 megacycles is your output impedance. That's why I've always gone half wave. But for spark making, the quarter wave seems to have the advantage, as we determined when we did both there, at Aaron's place, and we found out that the half wave gives you half the potential.
Yeah.
So my thing is, what I did is I just kept increasing the power until I got what I wanted. So it didn't matter if it's because if it's half the potential, then you're probably going to have more current at a lower voltage. You're going to have more current for the same power. So it won't give you as long of a discharge, but it'll give you a stouter discharge.
Yeah, very current rich.
But I know there is a way, by loading the high end of the coil and the low end of the coil, to modify the 4 constants of the coil, and maybe, if you do these experiments with this coil, this system is something that works. So ultimately, you don't want to change something that works, because it gives you your demonstrating capabilities. You got something you can show people.
It is, but this system is very flexible, so we should explore more and more into it. I mean, it's easy to change coils. And
my inclination, I wouldn't take any of this apart. I would start anew somewhere else on the scientific end, because you have something here that produces, fantastic display, and you don't want to take that away for a minute, because you might want to show it to somebody.
Sure. I tend to, Eric, I never take apart a piece. So for example, that primary coil, I didn't take apart the previous primary coil now to put this one in. I've still got the other one that I can put in, I can put back. So I do it as a kind of modular piece by piece.
Yeah.
And I take careful notes. So but I'm not averse to changing things here, provided I can do it in a modular way. So I can add, I mean the next real step, I think, on this system is really to put a pi-L matching network on the tube, and then run it at the series mode. Then
you're going to have to figure out that series mode is going to want to be connected to something that can handle a lot of current and not have any stray inductance.
Yes, indeed.
The parallel mode makes that easier.
Indeed, it does.
You don't have that, but so. The thing is, I mean, there's so many factors involved here that when we say one thing, then something else this is such a complicated.
I know.
That's why no one's gone this far with it.
Well, it's also part of the fun.
What we're dealing with here is an 8th order differential equation.
Yeah.
In its simplest form. In the most general form, if you look in the Bewley thing, I think it's something like a 24th order differential equation. And how are you going to find solutions to something like that?
Indeed.
Yeah.
Indeed. I mean, look, I mean, really, we have to approach it. We are approaching this on an empirical basis. So,
but I'm also doing it on a mathematical basis, on a daily basis. So trying to bring a meeting point together here. I mean, there is a way, I've laid all the mathematical groundwork for this. So I guess you could say the next part is experimentation, but it has to start off in the form of analog networks. which I've demonstrated,
Yeah.
prior, that,
Yep.
and which my Alexanderson antenna improvement is also an analog network. It's a concatenation of networks, 5 terminal networks, that basically, are like a low pass, high pass filter, any of those types. These are actually bandpass networks, but they're not filters. The transmission lines in between do not constitute an antenna. Yet this thing transmits and receives quite readily through the earth. So my inclination is to build like lumped analogs from the theoretical standpoint. What you're doing is more from the practical standpoint. You're after a specific thing where I'm trying to figure out a way, how do we come up with a theory that we can synthesize how to proportion a coil so that it is a coherent coil. Now, from the experiment,
Well, that's my question, but that's my question too. Do you have what is your sense in terms of the best geometry that brings it closest to the coherent condition?
Well, accidentally, Griffin got it almost right on.
You mean with the
Alexanderson coil? Yeah. So the variables is you can make the pancakes tighter. You can spread them apart or move them closer together. The diameter, number of turns, because it's not just a simple variable inductor or variable capacitor anymore. Now there's 4 things you have to vary rather than 1. So it's basically like a bridge T network or something, where you've got 2 separate paths of propagation, but you're trying to get them to line up at the right spot at the end. So at this point, it's easier, at least for me, to do it mathematically than it is to do experimentally, because mathematics can be adjusted, but adjusting the turns and the spacing on the coil is not as easy as throwing a piece of graph paper away and scrolling on another one.
Indeed.
Oh, there's one other thing. I need that microwave oven transformer data.
I already have that data, Eric.
Okay.
I was waiting for when we had a EPD Labs internal engineering meeting, then we can go over it in detail. But I already have all the data that you asked for.
Okay, yeah, because then Griffin and I'll turn that into a published engineering report.
That's absolutely fine. I've got the data, so we can discuss it at our next EPD Lab internal engineering.
Yeah, you could mail it to me too.
Would you prefer it, or I can call you and we can discuss it prior to that?
The thing is, I like doing stuff through the mail because then I got something I can handle. But yeah, if you call, well, we can do it on the live thing too, because that's like a telephone call.
Yeah, and also because then also there might be some.
But I like it when somebody sends me the sheets of paper, because then I can get that in my notebook easy and I can manipulate the stuff easier. If I got to play turtleneck at the computer screen through my bifocals, it's really difficult.
I understand. You end up going like this, looking at the screen close. That's okay. Yeah. Let's look. I have the initial data. Let's discuss that on our next internal call, because then there might be some modifications or additional thing you want me to take and stuff like that. Yeah. So let's discuss that. Bruce, I'm still conscious that there were more comments that you were making and that you wanted to bring up other things. You're on mute, Bruce.
And we are on 2 hours, 16 minutes.
And we're loving every minute of it, Aaron.
Okay.
You still got to open up for questions.
Yeah.
All right. Here's the last little bit. On that system I was describing earlier, the feedback coil to excite the grid, I incorporated that as a rotary coil similar to the core of a variometer, and I put it in the base of the coil.
Interesting.
And that worked very slickly. I mean, I could null it right out.
That's a good idea.
And yeah, just thought I'd pass that along to you.
Yeah, that's a good idea. That really is a good idea, Bruce. That would be, because that gives you almost infinite control as to the feedback.
It was really slick.
So just to check, you putting it right down here, huh?
In the base of the coil, of course, the primary was a flat spiral with like a very heavy cable with a 4 number 6 copper stranded
But are
wire.
you, but the frequencies are very different. I mean, are you suggesting that, I mean, I'm running here at around about 3 megacycles. Are you implying that I can use a flat primary coil and it will work at that frequency here?
I don't know.
It will. It will. And actually, it's preferable.
Really? What, a flat coil like they use in the low frequency situations is going to work here?
Yeah. That's
Oh, okay.
that's what I used, and the one I built out, the Integratron, was the primary. The primary consisted of an idler coil, which basically was a very high current, low voltage or low impedance parallel resonance circuit, where there's only like 2 turns of 2-inch copper strap, about maybe 2.5 feet in diameter. And then that was 2 turns in a spiral. And then in the middle was about a 7-turn bronze 1/2-inch strip spiral. That was the plate inductor. But the idler circuit did the tuning. There was no tuning in the primary circuit of the vacuum tube, because the magnemotive force of the idler coil was so intense that it over dominated anything that would be going on in the plate coil. So there was like perfect coupling. And then the solenoidal resonant coils, which were flat ones, rather than tall, skinny ones, they were short and wide. The pictures of this are floating around. Then they were moved in relation to this flat spiral arrangement to get the best mutual, inductance, more rightly, between the magnemotive force generating apparatus, which was the idler coil, and its excitation coil into the actual resonant coil, which then went to an extra coil. And I found through a lot of experimentation that there's a certain optimal relationship between the wavelength of the main resonant coil and the wavelength of the resonant coil, that all of a sudden this thing really took off. I mean, it really took off. So, and the one Aaron has is somewhat built on that idea, in that because there's a quarter, basically because one side of the coil has high current and the other side of the coil has low current, then how do you economize on the copper? Because if you wound the whole damn coil with 1/2-inch copper tubing, that wouldn't work out, because then, it would have all this extra capacitance and what have you. So what I did is you take the sine function and you break it at the 70.7 point. And so basically, if you take your resonant so-called secondary coil and you break it into one part, that where 70.7% of the windings are on the voltage side and the remaining windings are on the current side, then that standing wave doesn't cook the turns on the lower end of the coil, because it's a stouter coil. So
it doesn't get so hot down there.
Yeah, so you have an impedance concatenation where, one resonator leads to another resonator, leads to another resonator.
I've tried those myself as well. I know what you mean.
Yeah, but that introduces other complications, but
it does.
But I had great success in that. It worked out quite well.
So would you suggest here, going back to what you're also saying, Bruce, would you suggest here using, for example, that kind of spiral primary that you get when you use a thin gauge copper, copper tubing? Are you talking about that kind of spiral for this kind of frequency and geometry, or the kind of Litz wire type approach that I'm using here, but in a flat spiral?
I think at that frequency, I'm not so sure how much the Litz wire is buying you.
You want to use flat strip.
So flat strip.
Yeah, preferably bronze. Bronze has the best skin effect. Electricity, the magnetism soaks into bronze quite readily, bronze or zinc.
Can the
Where-
flat strip be a spiral?
What's that?
Can the flat strip be a spiral?
Yeah, edgewise,
So it can be wound
yeah,
edgewise.
band.
Okay.
Yeah,
Yeah.
like a watch spring. And,
Uh-huh.
never have the depth of the spiral any greater than a third of the overall diameter.
Okay. All right. About a third.
So typically, a lot of people use copper tubing because you could just buy it at the store and it's already in a box and a
And
spiral.
it's easy to
Yeah.
mount and stuff
Yeah,
like that.
easy to
Yeah.
mount and all that, yeah.
And this would
But
probably
flat strip is the best. Flat strip makes the best
Mhm,
economic use of the metal. And if you use bronze, because at these frequencies, the depth of penetration is only about 0.03 of an inch.
yeah. I must admit, I used the flat strip on the pancake coils that I use. You remember the
Yeah,
ones I showed you?
and another gross misconception is just because wire is finely stranded, it's Litz wire. That's not true, because all the conductors are in contact with each other, and it's
They don't have a.
still
They don't
signals
have.
the magnetism it out. The
Absolutely, they don't have an
best Litz
outer
wire-
insulator.
Yeah, the best Litz wire you can get, what I've used in the past for speaker cables and stuff, is a key telephone system telephone cable, because the conductors are all interleaved in such a way that that cable, if you hook all the conductors in parallel, it's Litz wire.
Mhm.
So if you can get a piece of telephone cable that doesn't
Mhm.
have too big of an outside diameter, like the key telephone, of course, none of that exists anymore. But at any rate,
But if you can find it, that's the best stuff
well,
to use.
I got plenty of it here. I made sure of that. And I got a 2,000-foot roll of 8-gauge true Litz wire.
Uh-huh. Now you're showing off now.
Not to be used indiscriminately, but whenever Griffin gets to the point, and myself, that the Alexanderson coil is fully quantitized and we're going to go all the way down to the bottom of the band, that's what that wire's for. For something like with these 5 kW AM transmitters I have. Then I've got some Litz strap that's a 1/4 inch thick and 3/4 inches wide for the big kiloamp stuff.
Uh-huh. Cool.
I didn't get the whole roll of that, but I do have about 50 feet for big heavy duty primaries. But what I learned in the Navy, the Litz wire is useless above 3 megacycles. And I learned from Steinmetz that just because the conductors are stranded does not make it Litz wire. So
Mhm.
I think at this
Indeed.
point we should call it QRU and go to questions.
I agree. Although let me just
forever on this.
Bruce, if I could just clarify one more thing. Are you saying that your feedback coil was actually inside the secondary coil at the base?
Yes, it was. I'll send you a picture of it.
That would be great. That would be good to see, because that would be a really good idea for tuning this type of system.
Yeah. Okay. I'll send it to
Right.
you.
All right, brilliant. Thank you, Bruce. Thank you, Eric. Thank you, Bruce.
Question time. We haven't
Okay,
exhausted.
let's see. I'm gonna stop this screen sharing. We're back in the middle there. Okay. If anybody has any questions, down at the bottom of your screen is a little smiley face that says reactions. You can click that, and then you can raise your hand, and then we can get you unmuted, and you can ask your question. Just say who you are.
And gentlemen, if I can just interject, this is Justin Miller.
Yeah.
And in the interest of time, not really going to give very much of an update, but I want to say this is an absolutely brilliant call. Really appreciate the interaction between the people
Flying a
that
helicopter.
we haven't seen to that level. Yeah. But I want to say that to the audience, to the participants that are in this call, it's some of what was just covered was so deep technically that it is over a lot of people's heads. I understand that. It's awesome to see, and I really appreciate sharing with the public here that level of interaction that we just watched, and look forward to seeing a lot more of that and more of that in the internal call. So, with that, if anybody wants to contribute, you can obviously see what EPD Laboratories is doing, what we're about. And Aaron gave the addresses, ericpdollar.com. We very much appreciate it, and I'll turn it back over to the group. Thanks.
Thanks, Justin. Okay, let's see. Looking for okay. And if we can keep the questions and answers as brief as possible, it just gets harder and harder to render the longer and longer that it goes. Plus, Zoom records these in not cinematic 4K, but like 3.8K or something like that. Then so I got to re-render it at half the resolution and then add stuff. So it's quite a process. But go ahead, Dylan, asking you to unmute here. And you can.
Can you hear me?
Yeah.
Can you hear me? Yeah, good. So my first question was for Eric. We had said that there was a chapter.
Too loud.
Too loud. Oh, sorry, my mic a little low.
Turn the gain down a little bit.
Is that better? Is that better?
No.
Little bit, maybe microphone not so close to your mouth or something. It's real amplified.
Yeah, I'm using headphones, so okay. Better or still too loud?
Still quite loud.
My goodness, okay. I don't know. I'll talk a little bit quieter maybe. We had said there's a chapter in Unity that has an 8th order differential equation, and then you said also that there's a 24th order. What chapter is that? Do you remember?
I couldn't understand any of it.
I didn't hear that. I didn't hear that.
I can't hear it. I can't hear it either. Dylan, if you want to go ahead and type your question into the chat, I'll read it and I'll go ahead and take somebody else real quick.
Okay.
Yeah, it's just all kind of muffled, distorted kind of sounding. Okay, James M. Go ahead, James.
Hi, really appreciate. Can you hear me? Can you hear me?
Yeah,
Yes.
nice and clear.
Maybe I've got.
Go ahead, James. What's your question?
Oh, great. I could kind of make
I've lost it now.
Yeah, it's in.
You're cutting out.
Yulee chap. I had some question.
Go ahead, real quick, James. It sounded kind of intermittent, like it was cutting off and on.
Yeah, it must be lagging. We're interested in the Bewley discussion regarding the coherency condition.
Okay, can you hear that? Okay, Eric.
Yeah.
What about it?
What book or chapter were you referencing there?
Let me get the book. Hold on.
Cool, thank you.
James, is that also asking the same question as
Yeah, he was asking the same question.
Dylan?
Okay, the book is called Traveling Waves on Transmission Systems. So this is the
Okay.
continuation, basically, of you had Steinmetz, then you had Alexanderson, and then you had Bewley. So Bewley was Steinmetz's final, how would you say, replacement. Or when Steinmetz died, Alexanderson went in the RCA, and Bewley was the last of the species up in about the 30s. So basically, it starts off with the book's in 2 parts, and part 2 deals with traveling waves in transformer windings, which is basically the subject that we're talking about here, the Tesla coil. So there's chapter 12, it's called the ideal 2-winding transformer. It does not develop the mutual inductance term, but instead it's a first order integral equation that doesn't look overly difficult, other than there's an awful lot of geometric factors involved. And then in this case, because there's no resistance and there's no conductance, let's see, where's more the resistance and the conductance? So for a transformer with no losses, it's an 8th order differential equation. For the transformer with losses, he does not develop the differential equation. This is probably too messy. So it is not, he does not deal with any resistance or conductance. He only deals with the energy terms. And then in chapter 13, transient oscillations in the primary winding. That's the one that relates to the Tesla coil. And you're dealing with resonance of one coil only. And that produces a fourth order differential equation. And in this, the mutual inductance appears as a dimensional coefficient of length to the length of the winding to the third power, which actually works out to be the dimensions of mutual inductance. So that equation, that fourth order differential equation, is the one that most readily applies to what we've been discussing as far as what kind of optimum characteristics can we get on a single layer solenoid or any kind of transformer coil of its own, whether it be stacked pancakes or a series layer. Substation transformers are stacked pancakes, whereas for radio frequency work, it's usually just a single layer solenoid. But as we found with the Alexanderson coil, which is a flat pancake coil, that geometry does bring the thing closer to the operating condition that we want of coherence. So if you're going to read the Bewley stuff, you got to have a pretty good background in mathematics and a very good understanding of electricity. It's not a book for beginners, but the thing that gets closest to the beginner approach is my presentation on the 20-to-1 scale model, where I go back into the people that preceded Bewley and kind of brought it more into algebra, and there's not any fancy higher mathematics in it to speak of. But nevertheless, it is not something for the beginner. For the beginner, you're just going to have to go through 4 years of banging your head on mathematics and doing experiments and all that. And then after 4 years, if the world's still standing, then you probably can begin on some of these other things. That's just, unfortunately, the way it works. It's not a it's not a social topic, so to speak.
Yeah, I'm aware of that. I studied math and physics in college, and I've been studying your work for probably a decade.
Okay,
And,
well, then we're off to a good start.
So I guess a question that I can ask that might relate to that. You mentioned that there's some connection to the Heaviside equation on transmission lines, as far as this coherency principle goes.
Yeah, it's called the Heaviside condition, where the time constant of magnetic induction, in other words, if you pull the plug on the transmission line, how long does it take the dielectric energy stored in that line to drop to 1/E? That time constant, and then you have the magnetic time constant. If you pull the plug on the transmission line, how long does it take the magnetic induction in that line to drop to 1/E? 1/E being 36.8% approximately, and E being the Euler number of 2.7 whatever. And so normally those two time constants are not equal. So in the undersea telegraph cable, it was grossly imbalanced. So the so-called mode of dielectric dissipation and the mode of magnetic dissipation were not occurring at the same rate, because the magnetic dissipation is based on leakage conductance, which was very low in the cable, but the dielectric time constant was based on the resistance of the wire in the center of the cable, and that was substantial. So basically, the magnetism got ate up faster than the dielectricity. So what happened is then the two time constants weren't the same. So if you sent a square wave impulse into one end of the coil, it would just end up amassing echoes at the other end of the coil, because of the internal mismatch of the transmission structure, the imbalance, it continuously sent reflected waves back as the forward wave propagated. And because of this internal incongruence. So Heaviside found if you added coils in series every so many miles to bring the magnetism up, and when you reach the point in which that the magnetic time constant and the dielectric time constant were identical, then if you put a square wave in one end of the coil, a square wave would come out at the other end of the coil, obviously much weaker, but it was still a square wave. And that was Heaviside's discovery. So what I've done is I've taken that to the next step, where instead of resistance, it's inductance, and instead of conductance, it's elastance. And mathematically, it all works out the same pretty much. So the Heaviside equation and the Heaviside criteria serve as an analog to what is trying to be done with the energy storage coefficients in these coiled windings. And I'm the only one that really knows about that or ever done anything like that, where the Heaviside stuff was very heavily worked over by Arthur Kennelly and Charles Steinmetz. So Steinmetz and Kennelly were the ones that made Heaviside's ideas work, where Heaviside was more interested in way out there fantastic mathematical theories, that compete with the relativist and all of that, and didn't really make things simple for the engineer. But Kennelly made it engineerable, and then Steinmetz took Kennelly's work. And so I have a 3-volume set that 2 volumes are already out that deal with this matter. And it's called Electromagnetic Induction and its Propagation. So that's a good first start in the matter. And then there's a number of popular presentations on the Heaviside situation that deal with it more in a popular manner. But that's essentially what's going on here. We're trying to get the longitudinal propagation constant equal to the transverse propagation constant. And when those two are equal to each other, then you have a distortionless network. And then when the two modes are together in consonance, then the magnification factor of the coil should skyrocket to values heretofore unachieved.
And so what did Alexanderson do with that? Did he write any books, or did he just sort of build the...
Alexanderson was kind of an in-between guy, and unfortunately he didn't write any books, but he left a legacy of his antenna, which is an apparatus that brings the transverse and longitudinal propagation modes into consonance. And I did experiments, and it indeed does that, and I build analog networks of his systems. There's a writing I did on the history of the Bolinas station that has a lot of theoretical work in the back. I think it's called Wireless Giant of the Pacific. I don't know if it's in book form or how you would get such a thing, but I know I did it, and I know it floats around, but I don't know how to access it. But I have the graphs of all the experiments and the waveforms and what have you. So basically, that's something
You're the missing link.
know about Alexanderson from the work that's written on him. But if you go to Alexanderson's patents and you remember the fact that he was closely related to Steinmetz, and that also that he preceded Bewley, and that he was chief engineer for RCA under the insistence of the U.S. Navy when RCA was formed by the U.S. Navy, you know that Alexanderson was a big player in all this. In fact, actually, he contributed greatly to the symmetrical coordinate system analysis of polyphase power, which was later fully developed by Fortescue. But unfortunately, Alexanderson did not write books. And unfortunately, a lot of people did not write books. Farnsworth did not write books. And Tesla was a real asshole. He didn't write any books at all. And he said, picking his nose and feeding pigeons, he should have been writing books, but he was one of those Europeans that was just too high on his horse. And so consequently, everything's lost. But Steinmetz was the exact opposite. He was a human coyote. He wasn't really fully domesticated. And he would disappear off into the bushes, deep into the forest of northern New York State. Nobody knew where he was, but he lived in his canoe, kind of like I lived in my Corolla, and had some little tree fort. And that's where he wrote his great masterpieces, which I doubt if anybody's really read much of anything at all. So his book on the subject is called Theory and Calculation of Transient Electric Phenomena, and the Heaviside condition is, even though he does not use Heaviside's name, but he does use a distortionless condition, is in the chapter called The Long Distance Line. So I think that's pretty much exhausts that subject.
Okay, thanks,
Well,
James.
that's what really appreciate it. Could I get one more quick question across?
Okay,
Yeah.
go.
One for Griffin, actually.
Okay.
So you've got that antenna, the elevated Marconi antenna.
Right.
I've actually just forgotten. Do you have that grounded to a dedicated ground, or is that grounded to mains?
I have a dedicated ground consisting of two 55-gallon steel welded barrels filled with water. They're buried at a depth of about 10 feet. So unfortunately, in the configuration of a flat top antenna, the dedicated ground plane should exist right underneath it. But due to my setup, it has to be allocated a certain distance away. But nonetheless, it does have its own dedicated ground.
Okay. And I just happened to watch your presentation on electroculture the other night. Are you still doing anything with that, or perhaps in conjunction with that elevated antenna?
I have not pursued it any further at the moment. Other matters have taken up priority, but nonetheless, in that presentation I gave an outline of the difference between AC and DC stimulated experiments involving seed growth. So there is some basis for any other replication with the means that I presented upon. I do know of some other individuals who have taken it further, so it is an interesting field of study, but I have not pursued it any further since I believe that was 2020.
Okay. Appreciate it. Thank you.
Thanks, James. Okay, and I think for the final question, I got two in the chat, one from Dylan and then one from Helen. So Dylan is asking Eric, I don't know if you covered this other than when you were talking to Adrian as far as the vector network analyzer charts, but he's asking squaring ohms and then taking the square root of that needs to change the units. Can you elaborate on that, and what reference do you have for unit analysis? Because I've never come across anything like that before. And then he comments there are some papers on IEEE written by Alexanderson. So that'd be for you, Eric.
Yeah, he did write papers, but never any books that I know of. But the thing is that the Z over Y square rooted is standard in any transmission line textbook. So the characteristic impedance of a line is defined as the series impedance in ohms divided by the shunt admittance in Siemens square rooted. So basically, you can't call the characteristic impedance ohms because it's a ratio between ohms and Siemens square rooted. It has the same dimensions as ohms, but it does not have the same coordinates. So it's called ohms anyway because people just tend to do things that are not right and then make it into law. Is because a Bell telephone scientist, very little known individual, was a major player in all of this transmission network analysis. His name was Zobel. And the fact that him and Ernst Gilliman, in his book, 2-volume book on transmission networks, communication network theory, I think is what he called it, also points out that characteristic impedance is a lousy term, but unfortunately we've used up most of the words to describe things. He tried some other words like immittance and what have you. That's where he makes reference to Zobel. So I decided at that point that because it's Z, and that it is Navy practice not to put an ohm sign on the end of a transformer impedance, but put a Z sign, that the proper name for a characteristic impedance would be Zobel. Coincidentally, what I did in defiance of physics and physicists, which deserve every bit of defiance that you can proportion to them, is they gave a magnetic unit the name Tesla, which really does not portray Tesla well, because his work was all in electrostatic and not electromagnetic dimensions. Is the elastance in K, rather than calling it per farads, which is kind of kanky, I call that the Tesla, and I don't care if the physicists like it or not, because it makes perfect sense, because that was the coefficient that Tesla was using in his transmission off the aerials of his Tesla transformers. That is not in farads, that's in per farads and reciprocal farads, just like this cockeyed arrangement of for admittance or susceptance or what have you is spelling ohm backwards and calling it Mohs is ridiculous, because the Europeans have the right idea. They use the word Siemens. Siemens was a big player in electrical development. His name belongs on something. And so I go along with the European methodology and use Siemens, which seems to be pretty much what the rest of the world does. And then the M for mutual inductance, well, I ran out of words, so I called that the Morse, because I think Morse was the first one to use. Him and Joseph Henry came up with the electromagnetic telegraph. So because it was a coil winding, which basically the turns are in a state of mutual induction around a core, I use the word Morse because it's been kind of customary to give every electrical constant or coefficient somebody's name. But in general, if I'm writing a paper or something for people that want to go along with the regular program, then I just use per Henry and per farad, but I don't use per ohm or Mo, ohm spelled backwards. I use Siemens. And also, I think it's become evident that I do not use hertz, I use cycles per second. And in the same manner, if you're talking about magnetic reactance, like the reactance of a coil at 60 cycles a second, that's not really ohms, that's henries per second. So I'm a real stickler when it comes to the semantics of units and dimensions and writing all the dimensions out. So basically, if I have, ohms per ohms, that would normally be called the numeric, but it's not. It's ohms per ohms. It's just a laziness not to clutter up, and nobody even writes the dimensions at all anymore anyway. But I do to make things a lot more understandable. So I think that kind of exhausts that subject. Do you have any further questions on that matter?
No, that was all that was posted in the chat.
Okay.
Two more quick questions. Well, one's kind of off topic about biology, but I'll ask it anyway. And then one about electrostatic generator, and then let's wrap it up. I do want to mention real quick. I'll just mention the websites after, and also in the video, I'll add subtitles also to Griffin and Adrian's websites. Okay, so Helen is asking, would you agree that biological space inside cells is approaching counter space closer than any natural physical system, because numerous biological membranes can be modeled as capacitors? What is the influence of the observer method of measurement in your electricity framework?
Well, the counter space idea seems to hold. It makes sense to me. And I'm not really, I can't say anything about the observer. That kind of gets into all that quantum stuff. And that's kind of like taking too much LSD. I just stay away from it.
Okay. And then final question from Tim. What is the status of the John Trump electrostatic generator and its relationship to the William Hyde electrostatic generator?
I don't know anything about the Hyde electrostatic generator, but When he
There's
says,
similar claims. He was
yeah,
making, yeah, he was making
I
some,
don't know. I've
okay,
never heard of that before.
okay.
But no, I don't know what he means by the status of the electrostatic Trump generator. Does he mean, have we built anything, or are there plans to build it, or right now it appears to be that no one wants to engage in that level of complexity. So it's sitting dormant.
Well, so, I mean, after we did the co-presentation with the Chris Carson one, then, last year, Haka Says did a presentation on, you know, his build on it. Currently I'm working with Jeremiah on finalizing the Tesla turbine, which has been taken many levels beyond what was shown at the conference. We just have one more thing we have to fulfill, and then, get that moving. But the Trump generator after the Tesla turbine is kind of priority for me anyways, because, you know, we're talking with Eric and it seems obvious it's the dream generator, absolutely suited for the Tesla turbine because of its high speed operation. And, you know, it's basically on the to-do list, and that's the status of it. So, yeah, I think I'm just going to screen share a couple websites real quick, and then we can go ahead and wrap it up. Going on 3 hours almost. So this emediapress.com, this is the my primary website. This has all the video presentations, books, and this search box at the top right is for presentations. And if you want to go to the blog, I think it's down at the bottom. Well, it's easier to just click on the blog. There's quite a few updates here. And then if you go to emediapress.com/energy times, that will forward to a page where you can sign up for Energy Times here. This is where most of the announcements always go out first, and I usually send it out simultaneously to Eric's list as well. But this is where all announcements on any kind of updates and stuff usually initially goes out first. Next website is ericpdollard.com. That's P for Paul, which is his middle initial. ericpdollard.com. You can go to the donate page here, and EPD Labs is a 501c3 nonprofit corporation, and its survival is pretty much based on donations. At the bottom here, you can scroll down. You can send checks or money orders to this EPD Labs address in Spokane. And I just endorsed a check, send them down to Nevada. There's a way to donate by Bitcoin. And then there's a PayPal link. This is where probably 90% of the donations come in. When you click the PayPal link, it'll bring you to a page that will allow you to donate, you know, like a one-time amount, or you can click monthly, and you can do a recurring donation. Any help that anybody is willing to give that goes to running the operation and supporting a lot of the projects like what was discussed on this call. GriffinGBrock.com is Griffin's website. He keeps us pretty updated with a lot of his projects. And in the left side, he also has a PayPal donate link, and you can see with a lot of the experiments and different projects he's working on that the money is, you know, getting put to good use. So however you want to support Griffin, GriffinGBrock.com. And then also Adrian's website is am-innovations.com. And you're also able to donate by PayPal to support his work. These projects are very, very expensive, very labor intensive. And so, you know, obviously it takes a lot of money. So anything that anybody can help with is very useful in furthering these projects. And so both Griffin's website and also Adrian's website is a wealth of resource with a lot of information and blog posts and a lot of papers you can download and so forth. And so I think that pretty much kind of wraps it up. If any final words, Eric, Griffin, or Adrian?
No.
No.
I think we said everything for now.
It's all good. Okay. Well, have a good weekend. If you celebrate Easter, happy Easter, and have a good time with your friends and family. And we'll send out a post for doing a next call. Let's see, 1,
In
2,
about a
3,
month's
4.
time.
Roughly the 27th of April or something like that. And depending, I might do an extra call with Eric, whether anybody is able to show up or not, you know, like a live call. I know there's some other stuff Eric wants to just kind of get into some conversations about and everything. Oh, and I do want to mention energeticforum.com. If you do want to communicate directly with Eric, probably one of the quickest ways, and also we'd like to encourage more participation in the forum, is if you go to energeticforum.com. There's a Eric Dollard forum inside there. And if you either start a new thread or you post in one of the pre-existing threads, Eric is able to, he knows how to post in there on his own as well. So he can respond directly to you if you have any questions. So
Well, actually, that didn't work. So it's going to have to be the old way with letters.
yeah. Well, I saw a post, but nobody responded. So
I
people
couldn't,
are always asking.
I couldn't get the thing to work. It just kept fighting me, and I don't, you know, digital likes to fight, and I don't. So I don't engage in digital. I don't need any extra hassles in my life or anger. There's already plenty of it to go around.
Right.
So I
Well, I
answer
did that.
letters. Some
Yeah.
letters. Yeah. But I do read the stuff that's on there. So that's where the question about the mutual inductance came up. So I tried to answer it, and it garbled. So at any rate, I had plenty of time to think about that question. So I presented my thoughts on it. But if you send a letter, you know, unless it's just goofiness or, you know, you worship Einstein or what have you, you're going to get an answer if there's a question worth answering. I always do that. Might take a little while, but I always do it.
Okay. All right. Have a good weekend, everybody. We'll see you in a few weeks.
Aaron,
Okay.
thank you.
Yeah, go. Okay. Bye, everybody.
But
Okay. See ya.
Bye-bye.